Testing, testing. Hello. Okay, everyone. Good morning. I think we will start now, I think. Just checking with Eirik that we are live on the stream. Yes, we are. I think there are some people that are still wondering about trying to find this place, but they will sneak in eventually. Since we also have some people following the stream online, quite a crowd actually. That's nice. Many people wanted to join but couldn't make it here physically to Oslo today. I think we'll just get started with this workshop on with the exciting title, International Workshop on the Aesthetics of Ventilation Sound. And I'll get back to exactly this title in just a little bit. But it's fantastic to have you here, both physically in the room and out there. This is the plan for today. It's a workshop, though, so we should try to get into discussion. So that's also why there are some breaks, etc., in between where we can engage in interesting dialogue. And we may make some slight changes depending on how things are going, but in general, that's the plan. I should also say that for those following on the stream, it's mainly what's happening here in the auditorium that will be streamed. So the activities down in the lab will not, unfortunately. And of course, also you'll miss out on the lunch and the fika and these other things. But anyways, also the people online are very welcome. But let's get back to the title and what this is about. But first, a little bit about RITMO, for those of you that don't know who we are and what this is. So RITMO is a so-called Center of Excellence in Norway with the title Interdisciplinary Studies in Written Time and Motion. And I'm the director of this center, in addition to being a professor of music technology here at this university. And we are now physically located in the same building as psychology. And that's also because part of RITMO belongs to psychology. But there's also a substantial amount of people at RITMO coming from musicology. That's also my home department. And we have people from informatics. So we have a very interdisciplinary or multidisciplinary group of people working here at RITMO. And just to kind of, for those of you that are not so familiar with this, we think about musicology as the study of music, as simple as that. There are other definitions of this as well, but that's our approach to this. Then psychology is the study of the mind, and our interest is particularly the embodied mind. And then we have informatics, you could say, is the study of technology, which is the study of arts, crafts, and tools. And this kind of summarizes quite a bit the approaches and both the theory and the methods that we are working with here at RITMO. So our vision is to expand our understanding of written as a fundamental property of human life. So written, then, how do we study these things? Well, we like to say that we study this from the softest soft to the hardest hard, where soft would be more on the humanities side of things, where we read and write books, but also engage in various types of musical activities, including also sound analysis of various kinds. Then we do various types of interviews, questionnaires. Over in the measurement side, we do a lot of eye tracking, motion capture, brain measurements of various kinds with EEG, FNIRS, fMRI. And we also do quite a lot of machine learning of different kinds and some robotics as well. And in recent years, we even put in a little bit of life science here, working with biologists on cellular motion based on sound as well. So that's kind of the summary of things. And the nice thing is that at RITMO, we have 60 active researchers, and they're all coming at this from different perspectives and have different expertise. So we try to put together teams where you can combine all these methods in different ways. But then, ventilation sound, how does that fit into this thing? Well, this is the ventilation channels in my office. And they are so exciting that I decided to kind of spend quite a lot of time on this, measuring them and recording them of various kinds, and even then organizing a full seminar about, not necessarily about these, but although we can take a tour and listen to them later on, but trying to figure out what's going on here. So the question then is really, what does this sound like? And it doesn't sound that fantastic in this recording, but I have a recording still so that you can listen to it. But it sounds like ventilation sound, although quite loud. And so it goes. But then you can say, well, is that particularly interesting? And well, that's the thing. It's not particularly interesting, but it's there all the time, and it's very present in my daily life. And it does change as well. The pitch changes, and it changes based on the time of day of various kinds. And then at now it changed a little bit, but it used to be at 4:45. Then suddenly it would turn off, and then you hear this on. And it would be, well, not really quiet, but it would be no ventilation sound any longer, at least. And that's a very strange feeling, that when you're sitting there, and suddenly then you feel that something is kind of changing around you, both physically and mentally. And this got me thinking about what's really going on here. And I mean, when I spend, well, 8-9 hours in my office every day, and if this is what I'm listening to, and then suddenly at the end of the day when it turns off and then I feel this kind of relief, well, is that something we should think about? Perhaps. Okay, so that was something that inspired this thing. And but then written, then does this have anything to do with written? And well, we'll see. We will have some more examinations of ventilation sounds later today in the program, but just to give you one quite extreme example, and this was from when I was on vacation this summer, I came across a ventilation system in Sweden, in Stockholm. There was definitely something wrong with this one, but let me just play you this. And this was actually in a hotel in Sweden, in Stockholm, and you can just imagine sleeping next to this thing. I thought it was quite fascinating because you had this rhythmic pattern going there, a really undulating thing, and it kept on going. Fortunately, this was a little bit away from the hotel room I was sleeping in, but I heard it out in the corridor, and it was quite intense. Fair to say that I did record this with a directional microphone, though, so it's quite extreme now, but still it's interesting to see the rhythmic patterns also in these types of systems. Now, okay, why am I interested in this? Well, first of all, my professional life has been surrounded by sounds of various kinds. I've been playing sounds as a musician, and I've been analyzing sounds, and I've been particularly interested in looking at what we call the action-perception loop of people, how we, body and mind, interact in our activities of various kinds. I'm also interested in the relationships between people and how they engage in particularly musical collaborations, so dance and other things together. And now, more recently, then I've become very interested in how we also interact with the environment around us, including people, but also spaces like the one we are in right now. So this has kind of been an inspiration here. And you can say that I've been then, more as a timeline, I spent the first part of my career on studying more large-scale body motion of various kinds and making instruments, and this is summarized in this book called Sound Actions that came out a couple of years ago, summarizing a lot of that. So, and this is available open access if you're interested in having a read. Then, after doing this kind of large-scale motion for some time, I got interested in standstill and not moving, really, and how that's what happens there, and how sound and music influences that. And I'm currently writing up a book called Still Standing about all of these experiences. And as part of that, I got interested in spaces of various kinds. And this was because in 2023, I decided to stand still every single day to work on this book manuscript. So I would stand still for 10 minutes every day, measuring myself with a mobile phone and also recording the spaces with a GoPro camera and an ambisonics microphone. And I stood still in many different spaces throughout the year, of various kinds, every day. Many of them were cool and exciting, but also many of them were just normal rooms, like seminar rooms here, auditoriums, living rooms, etc. And one thing that was quite prevalent in many of these spaces was that there are ventilation systems in many of them. And I got interested in trying to figure out, okay, what's really happening then in these spaces? Because this became very clear to me when I was standing there listening to this. In this case, you even have stereo ventilation here with the channels here, so it's quite interesting. And then I heard this term HVAC that was totally unfamiliar to me, but I then learned that this stands for heating, ventilation, and air conditioning. And the reason why I may not have heard about the HVAC as such is that in Norway we don't really have that many HVAC systems as such, because the heating is mainly done with burning wood or some kind of other type of heating thing that we have in spaces. So in most of our systems, at least as far as I understand, the heating is not really part of the system itself. That's this kind of separate thing we're doing. But the ventilation is there, and air conditioning, given this country, we don't really have that much air conditioning in this country, just because it's not really that warm in general. So most often we have ventilation systems of various kinds that are more for blowing in air. But then, what's the role of these then? Well, that's what I want to figure out, and that's why I have you here today as a group of people to help me figuring these things out. Because first of all, ventilation systems, they are electromechanical or mechanical installations that we have in our buildings. They are important for giving us oxygen of various kinds. They're also it's almost more metaphorically perhaps, but it's an interesting way of connecting indoor to outdoor or outdoor to indoor. For example, at home I have a passive system, it's just a channel, but I can hear the birds through that channel, so it's an interesting kind of opening to the world in a way from inside. You could also think about it more metaphorically about connecting people. I'm not really exactly sure how the kind of ventilation tubes are going, but at least in my old office down in the Department of Musicology, it was somehow connected to one of the rehearsal rooms in the basement of the building where we had drummers playing drums. And then that went straight into my office, 4 floors above. So that's also a way of connecting people. And then, of course, you can think of it as causing stress and or relief dependent on the quality of these things, and possibly many more. So these are some of the interesting things that I find about ventilation systems, and it's kind of inspired this workshop that we have here today to try to figure out, okay, what is this and what can we do with it? Now, many people have asked me what type of method do I use and we use when we explore these things, and I'll just briefly explain that so it kind of to frame this workshop as well. And I like to think that we work both on the nature and the culture side and try to figure out what's happening here, and I'm not thinking about this as 2 categories, but more as a continuum in a way. And I like another continuum as well between art and science, where we can think about different types of artistic and scientific practices and how they can coexist and work together. So on the scientific side, we write publications, and on the artistic side, we create artworks. But then, of course, there are other things where we can use scientific methods to create art and use artistic methods to create science. But also then different types of things in between that where we really see quite a lot of overlap. And that has kind of highly inspired the work we're doing in general, but also this particular workshop. And that's also why you see in this program here, you see a combination of more scientific and more artistic things, because I really want to kind of bring you together and talk so that we can talk to each other and try to see, okay, what's really going on here. So with that, I think I'll stop the introduction and leave the floor to the first talker, Anders Homb from SINTEF, talking about, well, just giving really an introduction to ventilation systems, what it is. I thought that was interesting. So, yeah, thanks for coming, and then over to Anders.
Yes, thank you for the invitation, Alexander. It was quite interesting to get this opportunity to present something about what we are working on at SINTEF. Actually, I represent both work from NTNU and from SINTEF. SINTEF is a research institute, private soda, and NTNU, you may know, is a university stated in Trondheim. So for several years, I had a professor position at the institute, and I had a lot of master students also working on HVAC noise then. I educated students in building acoustics. So this presentation will be on noise, the acoustic part, actually behind what you see from these terminal units, behind the mechanical and the acoustics behind the system. So what I think to bring in today is a short introduction. Of course, a lot of things around noise sources in the system, but components in the system also, of course, attenuate noise, both generate noise and attenuate noise. Briefly about prediction methods available, and look a bit more into frequency spectra and SFP factors, which I shall explain a bit later. And finally, something about alternative concepts and a bit of summary. Then to the introduction. Maybe many of you are familiar with some of these important definitions. The sound pressure level, frequency dependent level, of course. What we perceive in the room is the sound pressure level. But with respect to technical installations, we work inside the system, then we need to handle the sound power level. So all the calculations inside the system, it's on the sound power level. When the sound comes into the room, we calculate the sound pressure from the sound power level. The sound pressure level may be A-weighted to perceive, like we perceive the sound as a human, and very often as a single number quantity, not in the frequency domain. Frequency, of course, you know. I think it's a lot of musicians here, so you're familiar with that. A wavelength is also an essential parameter because the wavelength of sound may be much bigger than the dimensions of the ducts and chambers and so on. Maybe also very much smaller, but it's a wide range of wavelengths, complicated for the predictions, actually. And then to the specific fan power, it's the ratio between the electrical power required to drive the fan and the amount of air moved into the room, moved by these fans. So in Norway, we have requirements on this for new buildings on a low level on this SFP factor to be energy efficient. So this is a driving component how to plan the HVAC system or the ventilation system. I plan to say a bit about requirements in Norway. We have relatively strong requirements on noise levels. It's given in a Norwegian standard. People from other European countries that have similar requirements, I think. Actually, all countries in Nordic countries have approximately the same values. In German and I don't know actually France, but maybe at the same level. We have relatively low-level requirement for school, ordinary classrooms, or for resident rooms and healthcare. A bit higher for apartments, sleeping room, kindergarten, and so on. But and a bit higher than for commercial buildings. You have two levels. You have this equivalent level, time averaging. This AT, time averaging, it means, and this maximum level. for the ventilation sound, the most interesting is this time averaging, because it's normally a steady state level, normally. This one, I think, maybe is very familiar for many of you. It's quite a funny figure there. The human hearing, you know. Of course, this sound pressure is expressed in dB to compress the scale. And in the figure you see a pure tone. This more or less a sinus signal. And the musicians, you have, for musicians that form instruments, you have numbers of harmonics, actually. So if you look into the frequency spectrum, it looks like the second or third figure from the top. A number of harmonics in different combinations. But when we go to mechanical noise sources, we have much more broadband noise signal. But still we often get narrow band peaks, more or less broad, more or less sharp peaks. This example is a vacuum cleaner. But if we look into a ventilation system, these peaks at much lower frequencies normally. But it depends. System, HVAC system, may look like this 3D figure to the left. Air intake, filters, heater, silencers, and so on, and exhaust also to heat, to recover the heat, the air out and air in they meet to change the energy, to take care of the energy. Therefore, for modern buildings, you have outlet and exhaust, inlet and exhaust pipes into every room, needed for giving the air supply to the room. The figure to the right is more on the plan sketch drawing of the system in 2D then. This figure is from a guideline, and the numbers in red and green and black is actually chapters in this guideline, so we can quickly move to the interesting guidelines in the paper. It's given this big detail. It's a Norwegian tool for planners. Noise sources, important, of course. We have these mechanical units, fan and blowers. But another important contributor is the airflow generated noise. If you airflow through a duct system, you get some airflow generated noise from silencers and pipes, bend and branches, dampers, and the terminal units. And of course, flow constrictions is very important. It may give a very sharp increase of the sound power level, orifices and perforates. The third part is about the sound radiation directly from the aggregate. I don't talk about that because that's normally far away from the rooms. Sometimes the duct wall can be a limitation. Noise sources is fan and blowers. This may look like this. Two main types of this. This is a centrifugal fan type, and to the upper right, and the axial fan, like a more propeller type. But this aggregate, which is very common to put into smaller or bigger buildings, is look like the lower figure there. Then you have put into all essential mechanical components, fan filter, silencer, heating, cooling unit, and so on, compressed into one box, or maybe big then, of course, but depending on the volume of air to move. Yes, I said two types of fans. This centrifugal fan is then again is a two undertypes, depending on which if you have backward or forward paddle of this rotating unit. The typical frequency spectra of this centrifugal fan has a very high sound power level at low frequencies, and decreasing against higher frequencies. But this axial fan propeller type is a quite different shape of the frequency spectra, but it's very seldom used nowadays. I very seldom seen this axial fan type in the buildings, but only some few times. So it's quite different to deal with the centrifugal fan or compared to the axial fan with respect to acoustics and attenuation. Prediction is we need to have a reliable level of the sound power from the fan. Actually, then we are really need to have data from the producers, the specific fan power. It needs to be adjusted depending on the volume flow of air and pressure loss and other parts, but still we need this specific power level. Look into a frequency spectra from a typical centrifugal fan may look like this figure to the right, with where we see this blade pass frequency, the lowest sharp peak, and the next one is the harmonics of this blade pass frequency. This frequency scale is linear. We often present frequency scale in logarithmic, but actually this figure is in linear, so it's a bit difficult to compare with other frequency spectra. Yes, so we have then pure tone components, more or less. Then to the airflow generated noise. It exists prediction methods. And then we need to take into account all the components in the system. For instance, silencers, really depending on the speed of air, 50 log speed of air. In addition, the cross-section means a lot, and a bit other correction terms. With respect to bend and branches, like this second figure from the top, also increase with 50 log velocity. There are additional parameters to predict the frequency itself and the radius of the branches, takeaway branches. Sharp connection is very unpreferable. Dampers, like the figure from third from the top to the right, 60 log the velocity. And the cross-section and correction term to calculate it. Terminal units, like what we have in this old room, it's more depending on the pressure difference between the inside of the duct and the room. And of course the airflow volume. So if you then look back to this log to the velocity, it means 50 log velocity means that if we double the speed of air, we increase the power level with 15 dB. 60 log V means increase of 18 dB. It's a huge effect of keeping the airspeed low. And you get the same difference with respect to sound pressure level in the room. We assume that it's a linear connection between the sound power level and the sound pressure level in the room. Yeah. Then to attenuation. Actually, the same components attenuate the noise more or less. Duct and bend, branches, cross-section change, silencers, and the reflection terminal unit, and we have also possibility to put in an active silencer. I'll tell you briefly about that later. Yeah, sound attenuation. No equations for me, but only talk about it. Duct and bend. It depends on the type of duct profile, if it is circular or rectangular cross-section. The circular is the dominating and the most preferable because it is much stiffer, so it don't radiate the same sound if you have need to take care of the sound directly radiate from the duct. But when you have need large cross-sections, they often also use rectangular to save space, because then you can have that format instead for it's circular. But I think also the circular one is much more cheaper in installing and producing. You will find the tabulated numbers on what the attenuation level will be, with and without absorbing materials inside the duct. Next, the branches. It's actually at low frequencies it's a quite simple equation to calculate it, but when we in some frequency it shifts, and to be a very complicated connection between the attenuation and the dimensions. So all in all, it's quite inaccurate to calculate the attenuation of branches. Cross-section changes, like this figure to the right, it looks a bit like silencers, but also used for different outlet inlet of ducts. But it's actually should be avoided because you get a very huge increase of pressure drop if you have big cross-section changes, but it's very positive with respect to acoustics. So you lose something and get something. Yeah. Silencers, like this, this yellow figure, depends on the solution, and very depending on what the producer prioritize, and price, and space, and so on. If you have a big space, you can get a very high attenuation by such silencers. But also it increases more or less than the pressure drop, so it's about how to tune in the air volume and the fan, the power of the fan. Yeah, producer data is very important then. Then we come to the more or less to the room, and these terminal units. But if you imagine there are ducts coming into these units, and the dimension of this is very small compared to this room. So we have actually a huge, what we call an end reflection. It's actually a high-pass filter. The low frequencies more or less reflected back in the system to a high degree, depending on the size of the ducts compared to the room. But this terminal unit, the producers may have put absorbing elements into it, and that's good. But you need to know that very often they take also, when they give data, they have data for the sum of the end reflection and the properties of the unit. It's important to be careful, so don't take this component twice. Then you are really on the wrong track. Yes, so this end reflection depends on the frequency very much, but attenuate then reflect the low frequency back in the system. Yes, then short about this active silencers. This cancellation system. You may have used a headset with active noise cancellation on a plane. It's actually the same principle. You put a microphone and a loudspeaker into the system, and you have a control unit, signal processing, to play back the waves in and out of phase to the incoming, and it works. But you get a high attenuation down the duct line, but in the opposite direction you get more noise. So you get increased noise that way and reduced noise that way. So there can be that can be a possible challenging issue. But I haven't actually seen active noise systems in the buildings I've been in Norway. But it's a good opportunity actually. You can tune in and attenuate specific harmonics or more or less broadband. Okay. Prediction methods. Different tools is available. The basic theory is given from some important textbooks and guidelines. But also there are developed software tools. I have a list of that. This is actually not updated recently, but the two on the top is actually producers of HVAC component, making they are simple actually prediction tools for used for the HVAC engineers to plan the system. They're relatively simplified methods and not too accurate, but it's actually difficult to get accurate predictions at all, except this SIDLab is developed actually in Sweden. Is a complex system, very advanced. Above there are Train Acoustics, actually an American. I think it's maybe the best opportunity if you have want to use US units. Then it's follow the ASHRAE standard. This ASHRAE standard is actually the more or less a Bible for many HVAC engineers. But we have also a DIN standard similar to that. Yes, but this one, this SIDLab, is mainly developed for industry, car, exhaust systems with much higher speed of air, and maybe also temperature. So I haven't seen it used by engineers in buildings so far, at least not in Norway. So yeah. Summary predictions. There are significant uncertainties in the total picture of that. At least plus minus 3 dB to expected from what you can measure afterwards. And it depends on both on the uncertainties, both on the noise generation and attenuation. Components and depends also on the measurement methods, but because you need input data on a lot of products, and how do they measure it? How precise is it compared to the standards, and how is the standard compared to what you have in our system? So it's actually you can't expect too high precision on these predictions. But if to be a bit more close to what you should get in the real building, you should try to do some predictions. Also, because you need this have this energy optimization requirement. At least in Norway, I don't know if it's in other countries the same, but yeah. Yeah, so results often debate when comparing with measurements in buildings. Yeah, so how we actually go to calculate? The recommended way of doing it is to start with one source, for instance the fan, and then to follow the attenuation component until you reach the room. Then you step to the next power source and follow the attenuation component to the same room, and take all your interesting sources. When you are ended that, you summarize the level, and you calculate finally some pressure level in the room. That's the way of doing it normally. So from the sound power level to the sound pressure level, the room size, the sound absorption, the mounting position of this terminal unit, and the distance you are from the source is important parameters for this prediction of this some pressure level. Do you follow me? Okay, good. I think I'm ahead of the time schedule. Frequency spectra. I think many of you are very familiar with it. It's the same signal in 3 different presentations. The black curve is actually the narrow band measurements. It's a 1 Hertz measurement. But when we then summarize the energy into 1/3 octave band, we get these red circles. Then we, of course, have to smooth out the peaks, but not too much. But smooth out many of them, actually, as you see. And when we summarize to octave band, you smooth out even much more. So then you are very often seldom see narrowband peaks as this blue curve. You see it's higher towards low frequencies, but you have no further very detailed information about what you are dealing with. So that's very we on the building acoustics we normally measure in 1/3 octave band. The requirement often in octave band. But if we need to study and get rid of frequency components, pure tone and so on, we need to have narrow band information. Yeah. So therefore I put, so I get rid of this narrowband answer, but I have some examples now on, we have been through a lot of troubleshooting project for different buildings. And 3 examples from schools, 3 different schools. Each of these figure, different rooms in the same school on each of the 3. The upper right is actually very broadband frequency spectra, but we still have a lot of some pressure at the higher frequencies. So the red circle is actually the very intrusive to the listeners in that room. This blue curve or blue area on the top there. If we move to the left figure on the downside, we have a totally different frequency shape. It's a narrowband component at approximately 50 Hertz, very high and disturbing. But also have some more energy in the medium frequency range. So that's actually very often to see frequency spectra like these 2 in the bottom here. The to the right bottom is shifted a bit more to the lower frequencies, and therefore I think it's perceived better. This to the right bottom there. But still you have to have a sufficient low total level. But high frequencies should be actually low. That's my opinion. Yeah, apartments. You may also find actually more or less the same. This is actually for three different apartments then. Living room, 2 living room, and 1 sleeping room. And one of them a huge peak in RPM of the fan, I think, this blue one. And the other one is airflow generated noise. Both of them, both the gray and the yellow, is quite disturbing. And you see the level, the A-weighted level about higher, significantly higher than 30 dB, up to 40 dB on this blue. But it's quite too high for a normal perception, I accept. Yeah. Yeah, it's fine. More or less the same for offices. Sometimes low frequency, high peaks, low, and you could note that this gray one it's my office. I measured a couple of days ago to compare it with this other. So it's a high frequency, more a medium frequency, the maximum peak there, but it's disturbing. So actually the same as Alexander mentioned, his feeling when the X-ray system clouds down in our building exactly at 16 hours. 0. Oh, nice. But then we have no exchange more, so it shouldn't be there for very long. So, but I recommended slope. I think should be more or less like this pink noise shape. You can accept higher pressure levels in low frequencies, but you still should have a smooth lower level towards higher frequencies without peaks, without pure tones and so on. Yes. Then to the specific fan power. If you actually need an energy efficient system, it requires then low speed of air and as small air flow volume as possible. Then you reduce, of course, we have a low speed, you reduce the airflow generated noise. That's pretty nice. But it means that you need very often very large duct cross-section to have this lower speed, because you need to divide it on more space. And the negative part of this is you have to increase very often then the story height. And story height, it costs money. So there are conflicting interests there. You can imagine that you, instead of have a huge circular duct, you can divide it into two or three smaller ones, and you save space. But then the cost of the installation will increase very much. So I haven't actually seen it, but an opportunity. The second part is you need low pressure drop in the system for saving energy from the fan. You can reduce the pressure drop by minimizing the use of dampers and silencers and induct absorbers, because they are important contributors to this pressure level drop, increased pressure drop. But if you remove too many silencers or attenuating components, you get increased noise. So we have really a conflicting issue between this SFP, space, and partly noise. SFP and noise directly is in parallel, more or less, but with respect to space and noise, and space and SFP is conflicting. So we have seen, for instance, numbers of schools where you need duct dimension like this one, and the story height very, very costly to increase that space. Alternative concepts. Instead of have ducts into the thermal units, you have the volume above this ceiling is a big chamber, and you have only then slits in the ceiling absorber to the inlet of the air. Maybe you can make more pretty solutions. This is actually from a recently built research building in Trondheim. It's called SEBLab, and then we have experimented with different types of installing HVAC systems, and to compare with the indoor climate and the responses from the people who have their office there. We will not focus on noise, but it's very interesting, and it's an alternative. And then you also, of course, save duct, and you have much less meter of ducts because of use this chamber instead in this bigger room then. it's not relevant for small room itself, actually, for bigger areas. Another alternative is, which is very common actually, is what you call displacement ventilation. You put the inlet of the air more or less at the lower level of the room, and the exhaust at the top, like the figure there. I think it's work relatively well for different types of buildings, actually offices and educational spaces. I haven't seen it for apartments so far. Yeah, I actually already at the summary. Yes, I introduced this important parameter is the sound power level, which is the main to focus on inside the system. And I've told you about important noise sources, mechanical sources. And this very essential part is airflow generated noise from different components. And the same components may generate noise, they may also attenuate noise. Active noise, silencer is an option, and when you then come to the room, you need to calculate the sound pressure level from the power level. Finally, you have actually a conflicting interest then between the SFP and the space and noise. Frequency spectra. At low frequencies, noise from mechanical components, they dominate the content of the noise. At medium and high frequencies, mainly because of airflow generated noise, mainly. There may be some harmonics even depending on the RPM of the fan, of course, but mainly airflow generated. So I think you should remember that it's very important to avoid pure tone components. They are really disturbing in the head, or high sound level than in narrow bands. Fluctuating sound pressure is also very intrusive. If you happen on like this one, you can listen to recognize this very well. And the same if the pitch is actually slow or fast change of the frequency components. It's also very disturbing. So that's what I plan to tell you about today. If you are interested in acoustics on ventilation, you have a number of references to read here. It's a mix of international and Nordic tools or guidelines. You find this Ashra handbook there. This is a very important basic, and the same with this VDI Richtlinjen. Beside that, we find the Norwegian, Swedish, and Danish guidelines or presentations. And this guy there, Obom and Eldon, the people behind this advanced prediction tool. Yeah, that's what I plan to present for you.
Thanks a lot, Anders. That was an excellent overview of things, getting us started and trying to think of all the different complexities involved in these type of systems. I don't think we should open for a big discussion right now. Rather, I think we will do this little artistic intermission now before we'll have a break. Then, of course, we'll have more discussion later. But as I said in the intro, we like to see how we can combine scientific and artistic approaches. And now I would like to invite Audun Bjerknes, who's a filmmaker, who got very inspired by the topic of this workshop to create a short film for us not only for us, but for the world. Well, I'll leave it to you to discuss this, and then we'll have plenty of time for general discussion also later in the workshop. So, Audun, over to you.
Thank you. Let's see. So, you experienced speakers. Which way does it go? Alexander. Yeah, right. There we are. Okay. All right. So, yeah, it's very interesting to be here. I saw the announcement for this seminar sometime, I think, in the springtime already, and I immediately got interested. As a filmmaker, I have continuously waged a war on ventilation sound. It has been annoying. I've had to quarrel with janitors to turn it off when it suddenly turned on in a place where we scouted it and it was fine, and then we come there in work hours and it's boosted up or something. We need to turn it off and find the person responsible. Or we need to move our shooting to a different location to avoid it. Quite a bit of hassle. Or I sit several hours, which I've done, of course, over the years, trying to edit the ventilation sound away from my footage. So when this conference turned up making ventilation sound the main theme, I got very interested, and I got even more, it was even more encouraging when I noticed that Ritmo is behind all of this. Of course, I mean, I've been working at the university for 10 years as a filmmaker, making films for all sorts of departments, from theology to theoretical physics, all sorts of subjects, so it's extremely interesting. And over the years, Ritmo has been a main supplier of projects for us in my department, and we've had extremely creative and interesting projects with Ritmo. So it was no surprise it's Ritmo and Alexander behind this change of angle that really got me interested. So my idea was then, and is now, to go back to my material, where I've tried to get the ventilation away. I have included the ventilation, and it turns out when I start to include ventilation, it turns out it has its own voice. It really has a character. It wants to tell things. It has, well, as you will see, it identifies, and it turns out it really, well, it identifies with a larger history, historical and cultural events that ventilation relates to. So, yeah, let's have a look. So I should get the studies. Let's see. Yeah, I'll move the window. Right, here we are.
Hei, hører du meg? Hei, hører du meg? Jeg er ikke langt unna. Du kan nok ikke se meg, men jeg er her likevel. Jeg kan ikke si hvem jeg er. Jeg har alltid vært med dere.
Hvem er du? Jeg er sykepleier her på avdelingen. Ja.
Jeg har mange former. I noen kulturer er jeg det aller helligste. Navajo-folket kaller meg Onya, Onya, Wakan. Du kjenner meg godt. Du klarer deg ikke uten meg.
Dere kan ha fortsatt.
Det var skummelt.
Jeg visste ikke hvor lenge jeg skulle lage å stå.
Nei, det var det som var skummelt.
Ja.
Når det gikk litt tid.
Jeg kan rope alt jeg vil, jeg hører ingenting der ute. Så.
Kan jeg prøve å stenge dere inne?
Ja, bare ikke lukk døra helt igjen. Den ytterste, altså.
Kan den gå i lås?
Det står ikke lukk døra, men du kan lukke den inntil, bare ikke helt igjen.
Vis meg hva jeg skal gjøre da.
Litt øyeblikk, Klara. Ja. Audun!
Audun!
Hjelp!
Hallo!
Jeg må på do!
Her har jeg ingen adgang. Her får jeg ikke puste. Det får heller ikke du. Her overlever ingen av oss. Testing. Testing. Noen klager over at jeg lager for mye lyd, men hvis jeg er borte, savner dere meg. Her er jeg helt borte. Endelig. Her trives jeg godt. Gjør du? Jeg er ikke tomrom. Tvert imot. Jeg fyller rommet med liv. Jeg våker over deg.
So within this, we can have lots of activities to be done here. On the Moringa Stelentena, we can start from...
Jeg finnes overalt hvor det er mennesker.
The castes mobilize based on their particular identity, but I think one can say that there's a material basis.
Jeg er der selv om du kanskje ikke tenker på meg. Jeg kan være rett bak deg.
Have not seen their lives improve materially as they would have liked to see. And I guess that, if one sits in the opposition, might...
Jeg har ikke vært på poliklinikken i det siste, så synes det er vanskelig å komme seg dit.
Han her trenger litt trøst. Jeg gir ham i hvert fall noe han trenger. Jeg dømmer ikke.
Hey, Kuhn, I hear you've become a vegetarian, but you're making an exception for flying squirrels. Why is that?
Yes. This says something about the extent to which you have to be committed to research. You could also say that it was part of a research methodology called participant observation.
Du kan snakke om hva du vil, for min del. Jeg bare er der, jeg. Så snakk i vei.
was a very important part of their identity. Hunting had become something they were very proud about, and that was why I had to eat the poor squirrel. But at the same time, the culturally Chinese majority living on the island was very much against it.
Visste du at i gammel hebraisk kultur så er det samme navn for vind, pust og ånd? Ruach heter det. Jeg tror at hvis jeg hadde fantes i gammel hebraisk tid, så hadde jeg også hett Ruach, sammen med vind, pust og ånd. Jeg tar vare på dere. Tar dere vare på meg?
Thanks, Audun. With that, I think we will have our first break. We have about half an hour now to get some coffee, and we also set up this video is running in loop down on a TV down at Ritmo. And for those of you that haven't been here before, so the main part of Ritmo is 2 floors down in that corridor there, and there's also toilets out in the corridor, up or down. And since this is a workshop, we would like to engage in dialogue, so feel free to say hi to a stranger sitting next to you. That's perfectly fine. And well, see you back in half an hour for the next lecture.
Yes.
Hey everyone, welcome back. I heard lots of interesting discussions over the break here. I'm not sure out there in the world you don't have the same availability to interact with each other, but feel free to put things in the chat, and then if we have time for questions at the end, we may also kind of try to get in some questions from the online audience as well. I should also say that in the last email I sent out to all of you, then I also said that you should bring your ventilation sound recordings if you have any that you want to share. So the plan is that at the end of today's program we'll have I called it a panel discussion. It's more a general discussion really together, and then we can share. You can share your ventilation sound if you have one, and we can discuss them here and together. So that would be nice to do that. And we're also planning on also making a hashtag that we can share sounds on, for example, freesound.org with ventilation sounds. I already put up a bunch there myself, so we can follow them. So that's for later. But now, I'm very happy to have Christine Guillebaud from CNRS here. So she's an anthropologist, been working on sound studies of various kinds for many years, and she's also on the scientific advisory board of my ambient project, where you could say that this ventilation workshop is kind of an offspring of the ambient project, where we look at indoor spaces more generally, also independent of ventilation sounds. So I'm very excited to hear your thinking about and your research on noise, more kind of in general, I guess. So please, over to you.
Okay. Thanks a lot. So first of all, I would like to thank you, Alexander, and the Ritmo team for this invitation. I'm very glad to be here and to take part to this workshop on ventilation sounds. I have to apologize because it's not a paper about ventilation sounds, but there will be some connection, in the anthropological issue. What is listen to noise, especially in Global South. So this presentation deals with sound in public spaces as it has specific effects on perception. So I will examine two examples of noise perception in Indian cities. The first focuses on the perception of what we call quiet areas, such as parks and other natural spaces within the city, while the second example addresses the indoor noise perception. It is a new study, still in progress, based on the study of a helpline for residents in India to report sound disturbances entering in their private spaces. So these are two phases of the question of perception of noise. So let's start the presentation with a short introduction. When societies are confronted with the topic of acoustic environment quality, societies around the world tend to consider sound mainly in its negative aspect of noise or annoyance. This approach is reflected in numerous recommendations and prescriptions aimed at reducing people's exposures to excessive noise levels and is promoted by international organizations, as you know, such as WHO or European Union. In India, generally ranking among the most noise polluted countries in the world, is no exception in this regard. Noise pollution legislation dates back to 2000. That means 24 years later, nearly 24 years, nearly 25 years now, these laws are yet to be fully implemented. So there is something difficult to implement about noise regulation. So as an anthropologist, I got this question first: how can this gap be explained? The ethnographic approach revealed that two coexisting conceptions of sounds remain irreconcilable. The first one is a cultural one, and the second one is the normative one. So I will try to give some ethnographic example of this difficulty of reconciliation of these two positions. I have widely documented the first conception, the cultural one, in the MILSON program. MILSON, this is a French acronym. Mille in French is 1,000 sounds. Anthropology of sound milieu, including the study of the commercial activities in public spaces, the perception of places of worship, and acoustic management in the crowd in station. I have recorded a lot of station, bus station, train station, analyzing how people interact in this particular environment, for instance. In Indian cities, vehicular traffic is quite dense, the din of horns deafening, and sidewalks and pedestrian areas nearly non-existent. To what extent can residents avoid or adapt to the ambient noise? This is a basic question, but it's not so easy to analyze the answer. My presentation addresses, so the first example, it addresses the ordinary perceptions of user of a park. In the capital city of Kerala, this is in southern India, when people speak Malayalam, this park is one of the rare parts of the city where people say they can move around they don't say quiet, they say peace, shandanam. The word quiet doesn't exist. This is peaceful. the equivalent to the term calm. So I used two methodologies. First, this is a very well-known methodology of commented walks, well-established practice in research and arts. And in this methodology, individuals are listening to a place while moving and walking. This is very important to move to comment the environment, because there are frontiers to comment. When we are sitting, there is no contrast. So that's why I was very interested to test it in this park. And walks invite people to understand their relationship to the specific moment they pass through a given space, and to assess this environment in relation to the urban fabric. So these are the 4 rules. I'm an anthropologist, so I don't use scales from 1 to 10 to ask people when they feel, what they hear. I had only 2 very simple questions: what do you hear, what do you feel, and have a very open discussion in situation. So that was the way I work on the field. And it was also completed with some decibel measurement provided by an open source phone application, Noise Capture, developed by researchers in acoustics based in France at the CNRS and at the Eiffel University. It allows to perform measurement associated with geolocalization. That was the first time, and it's a very useful tool for participative research. So I really appreciate it. I'm not an acoustician, but I was thinking it was important to get a kind of objective level of noise. It's not 100% objective, but as compared to what people say, it's a little bit more. So this map shows that the general configuration of the park is relevant for studying the ordinary perception of noise. You can see the configuration. It's just close the main way with a very loud traffic. So I found it interesting to ask 2 people to say about their feeling when they enter the park, when different sounds are mixing, the traffic size and birds, insects, breeze together. So I wanted to know about what they are selecting, what they're telling about this sound. So you can see that on the main route, it's really red. That means the decibel level is higher than inside. Nearby, there is a zoo. Here is an art gallery. There is a snack area. So it's getting more yellow. That means the decibel level is less. So we can see easily how the decibel is changing according to the space inside or outside or nearby the way. So here is the main route. We can listen to, I suggest to listen to a short extract of the sound environment on this main route. So, je pars du East Gate. Je prends le chemin habituel. So there is, that is the mixing I was talking about between insects, songs, and traffic jam. And so in this part of the park, people are talking a lot. So I was interested to know what they're talking to me. Here is the inner spaces when students come for studying. another space for sitting, meeting, discussing, other greeneries, and when people stand and appreciated the Shandanam, the peacefulness of the place. And some areas planted with vegetation where people usually meet and discuss too. So here are the 8 recurring themes. I will comment only 2. I mean the 4th one and the 8th one, the peaceful in general and the restorative experience. What is peaceful? Perception of the park are verbalized at moments of transition, mainly when crossing boundaries. The first boundaries in the entrance, where study participants expressed qualifiers such as following, so prashanta, nishabda, silent, peaceful. So they indicated the sound close to them, voices, people, birds, insects, breeze on trees during sound walks. And they rarely mention traffic sounds. Also, they were quite prominent in terms of frequency, duration, and intensity, in terms of decibel. So they have avoid in their perception the traffic jam. This fact that is this zone of transition is characterized as sweet, peaceful, demonstrate that there is a considerable subjectivity of their perception. And the configuration of the place involves a permeability to external sounds that are not commented upon the site. So participants prefer to speak of humans and animals. So the question was a kind of challenge to me. So this way of listening, could it be due to a considerable capacity for abstraction? Or might it be an effect of the place itself? Because people do not evoke the atmosphere as inherent to the place, but instead they refer to its sensorial qualities. Yet another model is needed for understanding this disparity instead of decibel analysis. These are a quotation from the anthropologist Descola. We were talking about the line between nature and culture. He's the one of main anthropologists that theorize this opposition between nature and culture. And here is the definition of what is a landscape. He defines a landscape as a process of metamorphosis. The deliberated transposition of an environment. Descola defined this process as a transfiguration that, I quote, occurs in situ in the form of an arrangement of the space or in visu, in the form of a scheme of perception serving as a model for this figuration. So for visual perception, figuration is a scheme of perception. So I was wondering, what is the transposition for sounds? So I thought about a kind of transsonorization of the landscape. It is not the external form where traffic sound dominates that is transmitted in the park, but in intention to feel the calm and peacefulness. Care is to be taken, however, to not make a complete abstraction of this environment. It is still perceptible, information that people also remark upon as such. The other regular comments about sound in the park is the question of amenity. Sound workers regularly indicate how the park atmosphere has a positive impact on their psychological state. That is a really important point. I have reported here the main definition given by the acoustician Catherine Lavandier and Pauline Delettre, in 6 points. These are the definition by acoustician what is a calm zone. So you can read it. So I was wondering, do the Indian people in the park, do they feel the same sensation of restfulness, harmony, contrast, feeling nature, feeling an inner world, feeling of freedom and space? The first one, the directed intention, and the third, perceived contrast, is really important in the eyes of Indian people in the park too. So there is something common to the people perceiving in European parks. But the other definition as what is nature are quite different. Natural elements are never identified as such. People do not oppose nature to the urban, which is one might reconnect or join in harmony. The people don't say, I'm in harmony with the nature in the park, I feel my own inner world. This is a very individualistic way of perceiving. In India, people, they are talking about their family, their genealogy, their friends. When they listen to the breeze, the insect, they remind their relationship with their close friends, their mate, their family. That is something that was that struck me too. The question of inner world and freedom as very individualistic too, individualistic notions too. People in India are more deeply rooted in their social networks. It flues their sensorial perception of sounds too. Perception of sensory environment relates to the theory of spaces for mental restoration. This is the other theoretic part of the work. What is a restorative experiences? Is there a universal way to define what is restfulness or restorative experience? Here is the very great work of Kaplan, published in 1995, defining the 4 factors when we are feeling relief or restorative experience. So the being away, the feeling of being away, the feeling that the space is extended, a kind of fascination, a soft fascination to natural sounds, and the question of natural compatibility with natural sounds. Here again, some of the discourse samples that I've collected in India align with the criteria of being away. People too in India feel to be being away in the park, and they feel also a kind of extend feeling, both connecting to something else as well as soft fascination. This is why the third being away, extend, fascination are in blue color. But the last point is quite different. There is no supposed harmony with nature. It's only slightly relevant to defining the park sound environment because nature is not perceived and included as such, but rather as part of a setting for experiencing through everyday social relations. So a short conclusion about this first ethnographic study on park. There are 2 challenging questions. The experiment has made it possible to demonstrate that the peaceful is not exactly a given, but whether the object of a process of transonization coming from people whose relationship to the place is invested with sensoriality and intention. Usually acousticians do not study the intention of people, and as a social anthropologist, we failed in studying the acoustic as a physical phenomenon. So we have to combine the 2 elements, sensoriality and intention. A continuum also seems to emerge between perception of peacefulness and a degree of mental restoration. And the main definition of what is restorative place, of what is a quiet area, has been stated mainly in European and North American cities. Some works are also carried out in South America, in Brazil, but it's mainly based in the North global. So this methodology is proven in urban settings, such as sound walks, commented walks, reactivated listening have only rarely been tried and tested in the global south. So this leads to an important observation. This category, are they really invariant or universal? So this is really important. I don't have the answer now, but it will be maybe for the discussion, what is quiet, what is restorative. Let's move to the second ethnographic study I've conducted recently. This work is still in progress. It's about the notion of mediation and the perception of people when they are staying home. It's not really an indoor perception, but it's a perception of public space entering in these private spaces. So I have conducted ethnographic research on such a program, NIS, National Initiative for Safe Sound. This is ruled in Kerala by a civic group made of doctors. There is no sociologist or anthropologist, but mainly they are doctors. This is really a health issue. Noise is really a health issue in India. So the program sponsors awareness campaigns, educational programs, recommendations for safe sound exposure. And one of the leading actions of NIS was the inauguration of a dedicated helpline to report a noise in public spaces. First of all, I want to remind three general points about the quantification of neighborhood noise in scientific literature, because it's a huge part of literature on noise perception. What is called usually community noise in acoustics workshops. In social sciences, we are talking about quantification of neighborhood noise. But the first point is that researchers specialized in this area mainly relied on government noise complaint data. That means some of which data are available online or in archives, coursed with other available databases using multifactorial analysis. It may cross, for example, noise perception and urban morphology, noise perception and density, socioeconomic data. So this is a well-known area of research. And the possibility of inferring from such a data presupposes an harmonization of collection that we have not in our case study, because it was a hotline with a register. It's not a government register, so we have to make our own collection. That was very challenging too, but we're still working on. The second point regarding neighborhood noise in scientific literature is that ethnographies of offline and how they categorize complaints are often fragmented because researchers often come late to the process. Statistics are based on pre-imposed thought categories and predetermined classification of sound sources. Usually you can encounter the same public spaces, traffic, house noise, mechanical sounds. They are predetermined categories. This makes it impossible to analyze how consensus is formed prior to the quantification. Noise is a category shaped by public intervention, which is shut in a black box of administrative performance matrix. So we were outside the black box, and we are in the black box. So that was very interesting study on that point. And the third point is that in our Indian cases, in our case study in India, we can't refine this type of statistical validation mainly because the noise complaints are not analyzed by governmental authorities. So the non-profit and civic groups do the little monitoring there is. That means I was talking about participative research in the first example. In the neighborhood noise, the civic groups, the association are doing the monitoring. That is a really important point. So it's really important to, as an anthropologist, to try to make a deep ethnography of this network of associations. I have conducted ethnographic in this hotline ruled by the NIST program. This was the first time in India the public had been given an outlet for talking about the irritating sound they are exposing to their daily life. It was the first appeal to foster what people say, I like very much this expression, the sonic citizenship. A sense of civic responsibility through mediation. The service was installed in the office of the Indian Medical Association, and helpline worker, his Jisha, the head of the helpline, maintain a register when they note some personal data along with details on the context and origin of the irritating sound. 2 years after the opening of the helpline, the head of the service, Dr. Shafi, gave me the register with nearly 442 calls that we have upgraded to 500. They have first recorded, and we started to entering it into an Excel spreadsheet and divided into 10 fields. And all the data was fully translated from the language Malayalam, the local language in Kerala, into English. Then, after returning to my place in France, I have developed plans for extracting descriptive statistics with my colleague, a statistician, an engineer, Brian Chauvel, in my university. So the initial form of the register didn't include all the information we needed. So we first chose to focus on dates and addresses and define the rules in order to extract relevant terminology that could then be used to classify colors, for instance, according to their religions and sources of noise. 62% of the calls are dealing with place of worships. That is really, it's not about, there is a lot of traffic, there is a lot of air conditioning sounds, generators, animals, dogs, but people are mainly talking about complaining against place of worship. Here are the main questions that we have fixed it. They are very simple. When, where, who calls the helpline, what do people complain about, who is being complained about. So I will, today I will address about the third, fourth, and fifth points. Who calls the helplines? We know that nearly 83% are men. However, within weeks of the helpline's opening, the NIST team decided to not ask caller age. So I don't have any information about the age of callers, so we cannot analyze if the people are older than younger. That usually we think that older people are more annoyed by noise, but so it was impossible to fit in this in this point. We used colors given name to identify their religious affiliation and classify them by faith. So nobody asks to people, what is your religion? But by analyzing the given name, you say that Paul is a Christian, or Prashant is a Hindu, or Muhammad is a Muslim. So we got this way of research to classify people by faith. So in the first step, I use my own field experience to code the association of each given name with a given religion. So I use for each line H for Hindu, C for Christian, M for Muslim. So it took time. And then we compare this knowledge with data and other categorization online. So, sorry. This categorization is given in the ProKerala. This is a very famous website when the future parents, they are choosing the name of their babies. So it helps us to confirm the association of each given name. So after the statistical analysis, we found that 66.5 came from Hindus, of course. 66.5% of calls came from Hindus, 18.5 from Christian, and 12.6 from Muslims. Related to the general composition in the population, Hindu are 55% in Kerala. That means that they are overrepresented among colors as compared to the general population. And Muslims, they are underrepresented. They are in general population nearly 26.5. That means they are less concerned by noise as compared to Hindu. And Christian, perfectly proportional, 18.5. What do people complain about? One observation emerged when we analyzed the language colors used for describing sources of noise and nuisance. Place of worship are the leading cited sources, I told, recorded in the registers. In other words, Hindu temples and people are overrepresented in the perception of noise. Let's turn to the relationship between colors and place of worship. That is the more relational question. That means the question of whether the noises people complain about differ according to the population category placing to the call. The question, for example, was, do people complain more about mosques and temples if they are Christian? Or is there any interconfessional logics? So it led us to study the connections between the cited place of worship and the religion and of person complaining about it. We found that 47% of the complaints concern temples, that means Hindu temples, but the proportion varies according to religious affiliation of the callers. It is slightly higher among Christians, 53.5%, of whom call to complain about temples, and much lower among Muslims, 22.2%. This is from an already small number. What is important to note is that the faith of people do not conduct their calling. Hindu people can blame their own temples. That is a very important point, because usually we thought in source studies that sound is already something in competition, a social competition between religions, between groups, between castes. In noise perception, there is no social competition. There is something that is higher than our own identity, our own face. That was really, I was very struck by that as a strong social anthropologist, And I was also thinking that there were a kind of competition, but that was not. A few words, this is the relational analysis. I remember. Just a few words about the categorization of other sources of noise disturbances. So I grouped the keywords in different category: amplification, house, music, fireworks, animal, school, traffic, huge number of words connected with enterprise. So you can see some motors, generators, but there are only few as compared to a place of worship. Mainly sounds commented are produced in the public spaces, and we have also analyzed the keywords as compared these three categories: pollution, noise, sound. This work is still in progress, so I just to note that the identified sources are linked to mainly to the public spaces and activities. People are calling from the house, but they are blaming public space sources. They are not blaming their own neighbors, close neighbors. That is also an interesting point. And the commercial noise and traffic also emerge as key sources. Here are the few concluding remarks. First point. Literature on complaints frequently finds that women are relatively more likely to take measures to protest noise. In Kerala, it's men who are overrepresented. That is an important point. That means that the dimension of social authority is in work in every noise problem. Difficulties tolerating intrusive sounds are not solely related to the sphere of exposure. They also involve publicizing or even officializing one's annoyance. So there is a social publicization of its own annoyance. That is why men are overrepresented, because they are not staying home in full day. Women are more important, but the relation to the authorities is made by men. Second, we produced our own statistic. This study introduced a relational dimension that is rarely addressed in work on official non-complaints. In government authorities, there is no such equation of relation in terms of face or identity. For color, it's striking to note that their complaints are mainly about Hindu temples and Christian churches, and that their religion has little influence on their decision to make a formal complaint about noise. It challenged, this is the third point, I will finish it afterwards. Sonic communalism is irrelevant to people suffering from noise, and their tolerance is no higher for the sounds of their own religion than it is for the sounds of others. When speaking of annoying sounds, people didn't indicate their referent identity, social group. So there is a new social category to analyze for us as a social scientist. This is what the philosopher Hélène Leuillet called an ethic of neighborliness. You can read her quotation. It's a social tide made of it's not first to closest to us. With this primary others, we are neighbors. It's making a common place. Being neighbors is not an association, but it constitutes a tie, nonetheless. I will finish by this point. With this point, noise and abusive sound are not a matter of inclusion or exclusion, or even the alterity that otherwise largely fuels social relation. It's a social awareness of what we call the common, beyond the acoustic characteristic of sound sources, and beyond the social religious affiliation of the concerned actors. Thank you very much for your attention. Sorry for the duration, it's a bit longer than I was supposed to do. But thank you.
Thanks a lot, Christine. I think it's really fascinating to see how you unpack the complexities of what sound and noise are. And as far as I know, nobody has done a proper anthropological study of ventilation sound. But I think it would be super interesting to take this approach that you have developed here and see how it can actually be used, particularly also about complainers. I think that's an interesting thing also, that who would actually complain, or in the case of ventilation sounds, if we're just all sitting in our offices and do not complain, that's but get grumpy and angry about it. I don't think we have time for questions now, so I think we will move then down to the lab, where we'll have another artistic kind of intervention with Natasha Barrett playing some sounds. So those for you on the stream, then you will not be able to join us for this. After Natasha's presentation, then we'll have lunch, and then we'll be back here again at 1 o'clock, when we'll have a presentation about materials, including some even materials that are in the room here. So we're very much also looking forward to that. But then now we can all take our things and walk down to the lab. Let's get going again. I'm trying to kind of shepherd people back from lunch. That's always always a challenge. Now, continuing this very eclectic program, and as you have seen by now, I really like to put people together that may otherwise not talk to each other. That's kind of one of the things we like here at Ritmo. And hopefully by doing that, we can also inspire new conversations and new projects and new ideas. Now we're going to something totally different again. And I'm very happy to have Stig-Ronny Fredrikstuen from Glava here today, which is a quite well-known Norwegian company making insulation. And I'm very much looking forward to hearing you talk about the material side of things. So over to you.
Yes, thank you so much. Thank you so much for inviting me here. It's very exciting, and as Alexander says, it's a bit different for us. So I'm looking forward to seeing your reactions and to tell you how we perceive these issues with the HVAC systems. For us, the sounds coming from the ventilation systems, we perceive all this as noise, and for us, we don't want this sound. So what we help with is to remove it. We will not work to adapt so that you'll enjoy the sounds. For us, it's noise. So what we do is try to remove it. I've made this presentation together with my close friend and colleague Halvor Berg, who is a concept developer for Glava. So you might see him is also very interested in sounds from both in buildings and from ventilation systems. First of all, Glava is a part of Saint-Gobain, a very large international company making building materials. Glava have been producing insulation products in Norway since 1935. And today we are approximately 350 employees. Glass wool insulation products made from recycled glass is our core business, but we will help with many needs for insulation products for buildings besides just glass wool insulation. I've been in the construction business since 1998, so it's beginning to be a while also. I've been working with technical insulation and only technical insulation in Glava since 2016. Actually, it was 8 years yesterday, so it's been a while. And I'm a part of a team of 8 dedicated colleagues who are only working with technical insulation. For you, I'm also a hobby musician. I play guitar and I sing. I'm the world's most basic guitar player, and if you let me jam with you in the key of E, I will play the hell out of the pentatonic scale. So, sound problems with HVAC systems from our perspective, it's the only thing I can tell you about. Anders here also touched this area, but here in Norway we have a building law who have some requirements that we try to follow and to meet. And this law from sounds coming from technical installations states like this: requirements for sound conditions apply based on the intended use and can be met by satisfying sound class C in Norwegian standard NS 8175 from 2012. So you recognize this from Anders' presentation also. So this is what we have to meet, and if we open a small part of this standard, you will find many tables and columns saying what kind of sound levels you can have for the different buildings and from the different sound sources, if you may. This example, and I will use this for my presentation, is for buildings for teaching purposes and the noise levels coming from the technical installations. Just see that this standard is the law says it's supposed to be from 2012, but it's been replaced by a 2019 version. I think it's a gap there. I don't know if the 2019 version is quite ready, and I think there's some. The law hasn't been renewed, but I think the content is the same for this, and the principle is the important thing here. In buildings for teaching purposes, we can see that there are 2 levels of decibels. The top level here, 28 decibels, is it's the maximum allowed average, and the 30 decibels is maximum peak, as I understand this. So I will use this 28 decibels as an example through this presentation. According to one of my favorite sources, Store Norske Leksikon, Encyclopedia, 28 decibels sounds like something between rattling leaves and whispering. And our question is this okay for you? Are you happy with the ventilation system that sounds like something between rattling leaves and whispering? Because when you are doing a project, if you are the building owner or you represent the building owner, if you don't tell the people who are building or making the contract with you what you want, they will, of course, make you the system that meets the requirements for the minimum. If you don't tell them that you want anything else than rattling leaves and whispering in your ventilation system, that's what you get. And of course, if you haven't specified anything else, you have to be happy with what you bought. So I've just made this to try to explain. Sometimes you use a main contractor who then will be responsible for meeting your requirements, and the main contractor is then responsible for the subcontractors, and will gather all this for you as a package, and you pay only the main contractor. So in this case, you have to tell the main contractor if you want something else than the rattling leaves and whispering, that I want something else. I want something better, or if I'm concerned about sounds, please follow maybe column B or A in the same standard. I think it's a good idea to use a standard, because then you can measure the performance later, and there's a system for that. You are also able to bypass the main contractor. Can also be an option, that you say to a main contractor, please build me a school or something, but I want to take care of the HVAC system for myself, because I'm very concerned about this, and we want the sound levels and such. So the one on the right here is a type of total contract, and on the left is a more performance-based contract. And you can have mixes of these, but I think I may be shot when I'm done, but I think in too many cases we use a total contract with the main contractor, and we say only to him that I want a new school, we need room for 500 people and 50 students, please build this for me, and they say okay. And you get the bare minimum, and maybe you're unhappy with that. So for the ventilation systems themselves, we've seen the same picture as this before here today, but in the machine room you have a fan, or maybe two fans, one for blowing air in and one for taking air out. But this fan can be a noise source. And this sound can sometimes be heard outside the building, maybe through a vent or through walls if it's loud enough. It can also go into the structure of the building as resonance and vibrations. It may be heard through walls inside the building or inside the duct, maybe through the duct walls and through the ceilings, and also, of course, through the vents, as we see in the roof here. And sometimes there can also be a problem with sounds going from one room to another through the ventilation system. Without the fan will not affect this so much, but you can hear something from one room to another through the ventilation system. So I will try to break this down and talk a bit about some of the different issues we see here. The first transmission through the ductwork. This is the sound inside the duct. It can be made by flowing air. The higher the speed, the more volume or decibels you will have. And a way to stop this sound is by using silencers. We provide a board which is made of glass wool with a glass wool tissue that the air can flow across, and this board will absorb sound in the same way as a sound absorber on walls and such, but this silencer is the same. So inside these pieces of ducts, these boxes, there is absorbing material where the air passes through, and it will absorb the sound. So for higher frequencies, we can use smaller silencers, which is placed outside, not outside, but out in the building. The larger ones, who will have more or thicker insulation, they will be able to absorb lower frequencies and will typically be placed closer to the machine or the fans. The thicker the insulation, the lower frequencies you're able to absorb. It works like this. I think you will understand, but the sound waves flow through the duct, and when it hits absorbing material, it will be absorbed, and the volume coming out on the other end will be less than when it came in. We had a filmmaker here earlier. I've made a film for myself. It's very high quality, and I hope we will get the plot here. It's quite advanced. We've been using 2 telephones, one for filming and one for sound. This is my hand, and I will put my phone inside this and just hear how effective these silencers are, because there are many manufacturers and such, but just listen. I think you will understand this movie. So, how did I do, filmmaker?
Good soundtrack.
We can also, this is a bit of a commercial, but in Glava we have a system called Klimavere. I have a small piece of this duct here, but we are able to build the entire duct system with recycled glass wool boards that will absorb sounds in the entire length of the duct. Every piece of the building will be able to absorb sounds, and we can calculate the specific fan power and such, and the dimensions of the duct. But as you can imagine, this will absorb a lot of sound, and we will also be able to avoid resonance from the material, because it's not metallic, so it won't vibrate. I will come back to that. If we are not, if we've dealt with the sound inside the duct, maybe we want to stop sound, what we have left. For absorbing is one thing, stopping for us is another. So the sound coming through the walls or through ceilings, it's a different principle. To stop the sound, the principle is that we would like to use gypsum. It's a heavy, hard, dead material that stops the sound from penetrating. We also want a gap between the 2 sides of the wall to avoid any resonance going from one side to another. And we also want to fill any gap with mineral wool to avoid cavity resonance. So this is the principle. Of course, you can insulate the duct on the outside. It will help to some extent. You can use advanced ceilings that will also help to stop the sound. But the principle is that we want to stop the sound, avoid vibrations, and avoid resonance. So there are many ways to attack this, because there are so many different places where the ducts are placed. But this is the principle for stopping sound. This is a small section of this presentation, but I think sometimes when we specify and engineer the systems, this can also be a problem, or and it's that having several noise sources will increase the noise levels. Doubling the noise sources will increase the noise, the dB levels with 3 decibels. So if you meet the requirements with 28 decibels, you're good to go. But maybe you or someone else also add more technical equipment with the same decibel levels. They also meet the requirements from the law. The results is not 28 anymore. It's in this case 31. This can maybe be ventilation. Maybe the other one is plumbing. Maybe it's more ventilation, different systems. And it can be something to be aware of for those who are calculating and making the systems, that more sources will increase the levels, even though one system will uphold the law or meet the requirements. And it can sometimes maybe be hard to find the responsible one for the customer not being happy, because what the customer experience is that the noise level is too high, but it's not the ventilation's fault and it's not the plumbing's fault. It's just an unhappy customer. So I don't know how big this problem is, but it's still a truth. Transmission or vibrations, flanking sound. I'm not really sure about the correct term, but often a ventilation duct needs to go through a wall or a ceiling or floor or something. Of course, it's not always in free air. So you have a hole in the wall, and you put your duct through this hole. And when you do it like this, there's no problem. This is fantastic. Everyone's happy. Of course, you will have a gap around here, so be sure that you fill this and try to stop the sound from leaking through this gap, and use an elastic material to seal this hole. But this is not an issue. This is great. But I see in many cases that the duct is placed like this, and here we have an issue. So now I will go back to filmmaking. I've made another movie, so get your popcorn ready and just enjoy this. There are some fancy colors here, and I will try to explain. This is on my kids' Lego table, so here I've used Legos to stabilize my phone and try to make an exciting video regarding ventilation. So when you hear this, this is the ventilation duct in free air, and there's no problems here. The problem we see when the duct hits the wall. See what I mean? So this is, I think this is a bigger problem than we might know. So I will just sum up. As Anders also was talking about, there can be some conflicting interests, because we want low air speeds, we want low energy, we want to use as little space as possible. And the duct sizes, the larger they are, the more they cost. So there are some conflicting interests here, but airspeed is a big factor for making sound. The higher the speed, the more sound. The system itself, there are many types of systems, manufacturers. Some are cheap, some are expensive. So the system will also have a saying in the quality that you experience. The diffusers or the vents is also, of course, a part of the system, but there are differences here. Some make more sounds than others, so it can be an idea to change them or to do some research before you install these. The layout of the system, is it a good flowing system, or is it an old system with lots of branches and bends and components that maybe not been correctly programmed or installed? So the layout of the system is also crucial for the sounds it makes. And as you saw, maybe the easiest example is the hole in the wall, but of course the installers are also responsible for for the final quality. And the room acoustics. If you have a sound in a room, it can be call it amplified if the room acoustics is not helping the noise that you want to, or the noise. We can reduce some of the perceived sounds with ceilings, sound absorbing ceilings, and also stop the sound from the ducts penetrating the ceiling. We can use technical insulation around the ducts to prevent sound from leaking, and there are different materials we can use there, but we can insulate the ducts from on the outside. We can use the silencers and absorb the sound inside the ducts and also in the rooms with the room acoustics. And the construction of the building, is it resonating a lot, or is it built in a way that maybe stops some resonance? Are the sound stopping walls good or bad? It will also affect how the noise is traveling through the buildings. So that was my presentation. Thank you so much for listening, and I hope you learned something.
Thanks a lot, Stig-Ronny, also for engaging films in there. We do have time for a couple of questions before we need to move down to the lab again, if there is anyone. Natasha, you look like you wanted to.
Yeah, thank you very much for the talk and presentation. I have a question. It's a general question. It also applies to the first talk of today, and about the Norwegian standards.
Yep.
Who actually decides on what these standards are? Because I've just looked on the internet and I don't really find information about who makes the decisions about the noise levels that we have to tolerate in our buildings. You probably know, as you worked in construction.
I think there are people here that knows more about that than me, but there's a committee, or it's called Standard Norge, Standard Norway, who are at least putting it together, but I know that they are working a lot with getting input from the call it the market. Maybe the one from the acoustic in behind, or maybe Anders also can fill me out on this.
I mean, I can imagine it's a compromise between cost and well-being, but you know, it'd be interesting to know what the considerations are actually to do with health and all these other issues and the cost.
It's a committee behind this suggestions for this standard, but it needs to be applied by the public authorities. So this 2019 version is not applied by the formal authorities. So therefore, the older one is still the real requirement level. And I guess that the reason is they haven't done any correlation to the increased costs with the new requirements. I think that's the reason for not applying still. So, yeah.
Yeah, and as a follow-up to that a bit, is there any estimates that we know of how many building, or how well do various sorts of buildings actually conform to these requirements? Because I'm sure I've been to many buildings which can impossibly have met the demands. And I feel like they're mostly sort of taken for granted as like, this is what the ventilation gods gave us and we can't complain. Or like even noticing that it is a problem. So I wonder, like, how is it enforced, and what can people do, or who should be the ones checking these things? Yeah, exactly. There's a powerless to this, right? Like, which is.
I have no number for this because we only get the complaints. So no one is ever calling us and say that we are very happy with our new ventilation system. Thank you so much for applying the soundboards to the manufacturer of this, because it's It's working fantastic.
That's why we need the hotline that Christine was talking about,
Yeah.
right? To have a place to call. But I think we will continue this discussion later on. But now I think we need to move again because we're going back down to the lab for another little artistic event. So, we will be back here. But again, if you don't leave valuables behind, leave your jackets. That's fine. But don't leave your wallet. Yeah. And then we go down to the lab for Maxime's performance. And thanks again to Stig-Ronny for his talk. Now we have been exploring listening to sounds and ventilation sounds in different ways and different approaches to analyzing these, either from an acoustical point of view, from an anthropological point of view, etc. And now we are coming to also more of a signal processing approach to analyzing these things. And now we have two Whitmonians, as we call them, with us today. That's Arthur standing here and Olivier sitting there, working on signal processing and machine learning approaches to sound analysis of various kinds. So, and I've asked them to talk about that or look at the ventilation sounds then and see what they can get out of this with some approaches from music, from a more music analytical point of view. So over to you, Arthur.
All right. Can you hear me? Okay. Good afternoon. My name is Arthur. I'm a doctoral fellow at RITMO. I'm today presenting together with Olivier, also from RITMO, about an exploration of indoor soundscapes with a still standing data set. So here's the outline. I will introduce some basics of the motivations research question and the data set, how we collected it, and some simple spatial analysis. Then I'll give it to Olivier for a more detailed analysis of the spectrum, tonal, rhythm, some music components out of the noises. So the story starts with motivation of Alexander, actually, to study how does the indoor environment affect us. And this has two aspects. One is the audiovisual characteristics of the space, and another part is how it affects us, which is the bodily entrainment of micromotion. So we want to capture and analyze different types of indoor spaces, and more importantly, we want to study the real-world rooms. And in order to capture the space, we do want to include the spatiality and of the room. So we want to have some immersive recordings. And lastly, since the data was collected throughout the year as a daily practice, so we want the data collection process and the setup to be portable and as simple as possible. As a result, we have a simplest setup, but that still includes 4 different types of devices. There's a 360 camera, GoPro Max, capturing the 360 audio, the sphere of the spaces. There's an ambisonics audio microphone, the Zoom HC-VR, that is capturing the first order ambisonics. This is the audiovisual stimuli of the indoor spaces. And then for physiological data, we have a smartwatch that's collecting Alexander's heart rate and room temperature. And there's also a smartphone hanging on the chest of him, collecting through various sensors from the phone, including accelerometer, the brightness, and the loudness meter. And finally, there's a text description written by Alexander after each day's collection about what is the sound sources of each spaces and what is the overall collection process. And each of the recording session lasts for about 10 minutes. And as a result, we have the still standing data set. It's a multimodal data set, but it can also be think of as a fieldwork collecting different environments, and also probably a diary of each day. And we, in the result, have 365 samples And we cut it a little bit to make sure the component is clean without interruptions in between. So in the end, each of the recording is about 8 minutes long. And here we can see a sample. So this is a collection inside a laundry room, and on the right you could see this is the text description of the space. We have interior sound sources. We also have some exterior sound sources outside from the room. And there's also different visual components, the light, the blinking, and the washing machines. And there's also a general comment about the experience. And we also have the heart rate data and the motion data of Alexander. That's not shown here. We plan to do a release of all these data we've collected on OSF so that everyone can use it for their own purposes. You could use it for analysis purposes, for training your machine learning models, or use it for artistic purposes. We're still working on some data cleaning and privacy issues, but now we have the watch data available, but after working out with all these cleaning, it will be available on OSF. Okay, now over to some basic statistics related to ventilation. This is extracted from the text descriptions collected every day. It's not objectively describing whether ventilation is present in the spaces, but it's more of a subjective reflection of whether the ventilation in the spaces comes into the mind, so when it's noticeable. So as a result, about half of the collections, we mentioned ventilation in the text description, and it's actually the largest indoor sound source. So yes, ventilation systems are very important. And there are also some descriptions about whether the ventilation systems are quiet or loud, and or there's no specific loudness noticed from the ventilation system. So out of the 187 samples, when the ventilation sound is mentioned as the indoor sound source, about 37% of them didn't specifically mention the loudness, but about 60% do mention the loudness of the ventilation, and about 38% are quiet, the rest are noisy. So the loudness is an important aspect of ventilation systems. Apart from loudness, Alexander also mentioned some other characteristics of a ventilation system, which is typically not often stated. For example, the directionality. So in some of the rooms, the ventilation systems are sort of omnidirectional, and the sound is coming from all of the directions. But in some other rooms, it is specifically clear that the ventilation system sound is coming from a specific direction inside the room. And in some rooms, there are even multiple sources of ventilation coming from different aspects. So that is quite interesting and not very often mentioned, actually. And another aspect of the ventilation is, of course, the frequency. But a little bit surprisingly, it's actually not very often mentioned in terms of a characteristic of the ventilation systems. So only about 12% of the samples have mentioned the frequency as a characteristics of the ventilation system. And most of the time, it's saying that it's having a very specific low frequency component, whereas the mid or high frequency component of ventilation system is very rarely mentioned. Over to some statistics, since the data was collected throughout a year, so we can sort of having some summarize whether the sound of the indoor spaces is affected by, for example, the seasonal aspects, holidays, etc. But here it seems like there's no significant variances in terms of the loudness distribution along different month of a year or different time in the day. So this is a plot of the samples when were they collected in the day, and it seems like it's been quite constant throughout the day. And now over to ambisonics. We have some other guests in the workshop mentioned ambisonics as a very important tool to analyze the spatiality of soundscape. In this, so Natasha was mainly using higher order ambisonics, which is very precise in terms of the directionality. Here, for simplicity's sake, we used first order ambisonics. It's less accurate in terms of spatial location, but it's still, we can reconstruct the spatiality of the soundscape from the recording. And we can decode the sound at a specific direction from the ambisonics recording. For example, if you want the sound right in front of me, we can put a virtual speaker at that direction and then get the output as a mono audio source from that specific direction. So we could have a description of the locationality of the rooms by using the ambisonics. So again, this method is very similar to Natasha's. We find the peak energy direction at each frame, and we can make some visualizations like this. I just need to lower the volume because there's a very loud clapping between. Oh, so in the beginning of each recording, we recorded a clap for synchronization and also to analyze the room reverberance. It might be a little bit. So this is the same recording from the laundry, and as we can see, since the two washing machines in front are functioning, then we can see this directionality in the recordings. This is counting the numbers of each direction being the maximum energy, and this is multiplying by the multiplying the energy and adding up. So here we can also see this is the clap in the beginning. Oh, sorry, that's a clap. And if we sum energy up, we can see this is from the back. So with this with this ambisonics, there are many things we can do. For example, when the ventilation system is directional. For example, in this recording, in the text we mentioned that there's a noise from the speaker coming from the back left, and the ventilation sound is directional and coming from the back right, which we can see from this plot that this is, for example, the noise from a speaker, and on the right, this is the sound from a ventilation. And then we can decode the ambisonics at these specific directions and get some output like this. And in the directional output for ventilation, we can hear this tonal component. This is from the speaker, so it doesn't have the tone component. And now we hear the tonal sound from the ventilation. So it's around 1000 hertz. And in other cases, when the ventilation system is omnidirectional, we can avoid the directions with foreground sound activities and pick the direction with the least energy to get the omnidirectional ventilation sound. For example, in this recording, we have some directional noises from the lighting system. So it's thing, and that can be filtered out very much in the direction with the least energy. It's still audible, but it's much quieter. Okay, and now over to Olivier for more detailed analysis of the samples.
Okay. Thank you, Arthur. Can you hear me? It seems. So I will get back to the ambisonic analysis later, but first back to the initial idea. So I have been developing a framework for analysis of audio recordings for music purposes initially, especially initially for understanding of music and emotion, and that has been progressively used for different applications, and especially for diverse aspects related to audio and even to various signal processing. And I'm also interested in music transcription and music analysis, so I try to combine all together, and also I have interest in analysis of electroacoustic music. So when I was asked to look at this ventilation system, I found it very interesting to go further as a kind of further dimension. So I will show about this kind of music information retrieval, so this computational music analysis technologies that could be applied for this analysis of soundscapes, and see the limitations and how we can try to go further. And so starting from a simple audio waveform, so of course from the waveform you can see sometimes there are high peaks showing that there is not only the soundscape ventilation, but there could be some foreground events. So it's also something we would like to work on, to automatically somewhat detect sound object and to remove these foreground events so that we then can analyze the background ventilation. But of course this is challenging. But so then you saw this morning about the spectrum analysis, and here is represented like this morning in a logarithmic scale, amplitude and frequencies. This is, for instance, from this actual room for Schamling's salon, the ventilation from this room. We can start to see, so in black is the actual measurements. And then I did analysis of this data sets. Right now, not the complete data set, but then we have statistics so that we can compare this room acoustics in black with the median of the spectrum in blue and the standard deviation above and below. So then we can, in this way, have a first comparison. And we can see that, of course, there are these particular peaks that could be of interest, and we can make description of those peaks, the width of these peaks, the interval between these peaks. Yes. Maybe I don't need to show that. So then, for timbral analysis in this music information retrieval research, there is this idea first to, for instance, compute centroid or spread of the spectrum, which is a centroid is a kind of the point of gravity center of the spectral distribution, and the spread would be the kind of standard deviation with respect to this center of gravity. But actually, when you use this actual equation for this analysis of these sound recordings, where we could suppose that the centroid would be centered around here, actually, we have something like that. And what happened is that actually this is a logarithmic space, and actually most of the samples of this spectrum distribution are on the right of the space. So that's and because it's kind of subtle, it's not very loud. It's not like in some very high sound where you have one Gaussian that is very clear. Here, the sound, the difference of amplitude is a bit more subtle, so that the silence is not that makes such a difference with the high of the ventilation system. So that actually you can't get a clear centroid because of that. And also centroid, of course, is kind of a first simplification of the description of timbre, and could be of interest to go more into details about what is the spectral shape. And actually, for this description of the spectral shape, what has been often used is computation of this band frequency cepstral coefficient, MFCC. And so starting from at the top, you have this spectral distribution. Then we decompose each. So in a way, it's like this morning we saw summation of the spectrum across octaves and third of octaves. Here it's a bit of the same, but with a higher frequency resolution. We have these male bands. And for instance, we start to take 133 hertz wide bands, like for instance from 0 to 133. You sum and you get this first value on the left. Then you do the same for successive bands of 133 hertz, linear at the beginning, and then it gets logarithmic for the high frequency. So you get this shape at the end, this male band spectrum. And then from this shape, we have can make some kind of compact characterization of the shape by computing this cepstral coefficient. It looks very technical, but basically it's a kind of a new periodic description, periodic analysis of that shape itself, and you get this curve. But basically, it's a series of numbers that give in a very compact way the description of the spectral shape. And this can be useful, for instance, to compare timbre recordings. And for instance, here we can then turn this into a space. So here, for instance, I have a selection of ventilation recordings. The MFCC component and the principal component analysis we reduce into a 3D space. And we see a location of some of the sounds based on this similarity in spectral shape. Then we get back to this analysis of the spectral distribution and the spatial distribution with this ambisonic recording. And as Arthur mentioned, so first, if we start with, this is just a mono channel from this ambisonic recording, you have this spectral distribution. Then here it was the idea of taking the direction where there is a minimum of energy, so that we assume that that will be where there is no extra sound, that will be more like the ventilation itself. And so we reconstruct that signal from that direction, and we get this. One issue here is just that the gain is not the same. It's just a technical issue that for some technical reason, the gain is higher here. But it's not a problem because, of course, here also it's higher, but for the MFCC, it will be the zeros component. It will be the DC component that will be different, but the rest is the same. So now we have the spectral shape related to that minimum direction, which could be the ventilation sound. So then we can then compare, that direction is in red, you have the sound, you can compare with the other sound in the data set, and the same sound when it's the mono channel, so that's the 16 that is shown somewhere here, and so on. So it's just the first step, but that would be the idea to then be able to decompose this sound and focus on the ventilation. Then it's a bit of a simplification here, but there is in this MIR toolbox a possibility of having some kind of tonal analysis key estimation based on this Krum-Hansel research. There are some distinguished music cognition researchers here, so I don't want to, it's a bit simplistic here, but the idea is that we can try to do the same with the recording of the ventilation. You have the spectral distribution, so you can make it as a distribution along the different pitch classes, and then compare to this Krum-Hansel profile to have a kind of estimation of the tonality, of the clarity of the key, and so on. And so from these different samples, you can see some of them have supposed to be very clear tonality. So this would mean that you can hear some kind of chord here. So there. Yeah. And this one maybe, the other. Yeah, something like that. And some other are less clear tonality. But of course, I can play this one. Maybe it's just one pitch. So, but of course, the idea maybe is to get further into actually detect the pitch, and from the pitch compute interval distribution or interval analysis of the pitch to have something more detailed. But we could also have an estimation of whether you have a major chord or a minor chord, so if it's a sad or a happy room ventilation. So this is a happy ventilation. And sad one. But of course, this is more like a joke because it depends on a lot of factors. Then, of course, I didn't speak about temporal revolution of this. It was just like global spectrum of the whole. But then it will be very interesting to look at the detail of temporal fluctuation along each frequency. The first possibility or option that is often used is compute spectral flux, so which means that we compute the difference between successive frames. You compute the difference between successive frames, and you get a curve. So here you have to remove the peaks are due to some loud sound, but then when you look at the detail, here, for instance, you have some kind of signal that will indicate the fluctuation of that given signal. And you can compare these fluctuations between different ventilation sounds. But the idea is that we need to be more subtle. And for instance, track the pitch and see the fluctuation of the pitch and the periodicity. I will mention about periodicity in the next slide. But here we could see some periodicity of the oscillation for each frequency. Some other possibility, maybe I have to finish quickly, but some kind of spectral structural analysis that could also reveal about this fluctuation. So you have the spectrogram for the whole sound recording for each successive time frame, and you compare each time frame with each time frame, and you have this color red means that these two frames are very similar. So you start to see some kind of texture in the sound, some structure, so that here you have some nice pattern and so that you can compare some due to some kind of macro structure, some micro, and some like this fluctuation, this spectral fluctuation. This one is very nice. It turns out that it's from the yoga training room, so yes. And I have the sound, and this, if it works, it should work. And this is due to this rhythmic thing, that due to some heating maybe, that appears at the beginning, middle, end, this rhythm. So this is the last aspect that I would like to mention about rhythmic analysis, and we can get very into detail. Computing a periodicity of the dynamic of the signal, the onset curve for each successive time frame, and you have a periodicity. You can see, for instance, here you have a periodicity of 1 second. It's the same example. There were tatam, so every second. But of course there is datum, so there is a faster periodicity or so at maybe 1/3 of a second. And this can be kind of displayed in this way. So you have this kind of possible rhythmic texture for the different sound. This one is interesting because there is some kind of change. And this was this example where you mentioned some popping sounds from the sailing. It was just after some time, and these are the popping sounds that change kind of texture. So a lot of things that could be considered. It's just kind of a start of some research here. But yes, you can see that it will be very interesting to go further into some kind of more advanced transcription of these sound objects and so on. Yeah, so that's the idea. Thank you.
Thank you to both Arthur and Olivier for this, and it's very exciting to see how you're using the kind of more music analysis approaches to this material as well, and I think there's lots of possibilities there. We don't have time for questions right now, but soon there will be fika down in the kitchen. But first, Juliette is ready for us to do a little bit of performance down in the lab. So we'll do yet another visit to the lab, the last one for today, and then there is fika afterwards. And then after that again, we will be back here for some ventilation hacking. So now you're all excited to hear about how it's possible to hack a ventilation system in different ways. So yeah, but first down to the lab for Juliette's performance. Oh, okay, everyone. Let's get started again. So now we are over to the final session. So we have first a presentation by Maham and Ioannis on ventilation system hacking, and then we'll fade over to the just kind of general discussion about this, and then that will fade over into a little bit more of a just relaxed session down in the kitchen. Yeah, over to Maham, who's a PhD fellow here at Ritmo, and Ioannis, who's a PhD fellow at the Music Academy. So let's hear.
Hello everyone, I am Maham, and today we'll talk about vent system hacking. Now if you look at ventilation systems, they look plain and boring. For instance, right there. And we do fun things at Ritmo, weird things. For instance, I was just discussing this with Eirik, who's up there at the back, and he says that he has stopped questioning the kinds of things we do here. So, generally, a ventilation system works by pulling in outdoor air. It goes through a mixing box, it goes through a heating or a cooling coil, and then it is supplied into a room through supply vents. And then that air is then absorbed into the return vents, and some of it is pushed back into the outdoor areas, and some of them is returned into the mixing box. And I want to mention that here we have supply vents and return vents. In return vents, the air is pulled out, so you have suction, and in supply vents, the air is thrown towards you. The reasons for vent interventions. They're either used for noise reduction or for aesthetic improvements.
Yeah, at least I definitely got into this for reducing sound. I'm mainly from a guitar background, and I've recorded guitar for most of my life. Guitar is a very quiet instrument, so you constantly fight your secondary ensemble partner, which is always some sort of ventilation, weird crackling rhythm thing. Also in apartment buildings, having a home studio is tricky. And we're not allowed to tinker with fans, so one of the easiest ways to get around that is to augment the vent exhaust in one room and kind of create sound mazes, and I'll get back to that a little bit later, but it works surprisingly well because we're not allowed to tinker with airflow, but this way, airflow goes through, sound doesn't, so it's a very, very good improvement overall, and we'll get back more to that as well, and we can also redirect things with ducts and so on. Although they are waveguides, so they become like little instruments that kind of shoot all the sound in one direction as well, and there are ways of going around that as well.
And for aesthetic improvements, people use vent covers, which are magnetic strips that you can simply stick onto the vents. People also experiment with wallpaper, so you can simply cut out little strips and put them on the vent. And some more creative people out there, they go for smart interior design.
But these
Ioannis has strong feelings about this.
Yeah, very strong feelings. So this is soft hacking, if you can even call that hacking. This is just a bit of paint. We can do better. And also, it doesn't. Most importantly, it doesn't combine the two. It doesn't combine any noise reduction with aesthetics. So you'll still hear the same thing. So there's definitely hacking opportunities here. But we kind of starting out. It's a question of like, what can we hack? Why doesn't everyone always hack with their ventilation system? There are some real modification constraints, not just the physical obvious accessibility constraints. We can't always reach up or like open things up and tinker with things. And note that picture doesn't necessarily reveal that we actually performed surgery on Alexander's office ceiling. I'm not saying we did or that we didn't. But there are some like legal murky things, like what are you allowed to do? And there's a sort of culture of, you don't mess with vents somehow. Maybe there's this kind of public-private boundary in a way where there's a personal space, you can sort of put furniture in your office, but you can't, building structures off limits. Mostly invisible systems, you wouldn't even notice that there's all this thing up in the ceiling unless you hypothetically lifted some of the tiles. So there's some kind of like trained cultural docility around ventilation and a kind of feeling of powerlessness when it comes to mitigate. You just accept things as they are. I can sometimes, barely get a power extension lead at my office, so good luck sort of getting someone to sort of fix my ventilation system. It just gets accepted. And then the question comes up like, well, who actually defines these things? And especially in terms of health and all the indoor, sort of the health implications of constant noise pollution. It's not the most democratic topic, but we kind of want to open up the ideas of like what you can do with things, hypothetically, yeah.
For starters, we're using this thing called the action sound theory, which focuses on the relationship between physical actions and the sound they produce. And this concept is borrowed from Alexander's book, Sound Actions, which maybe some of you already know about. So here we have sound-producing actions, things that directly create sound, and we have sound-modifying actions, things which alter existing sounds. So some examples of sound-producing actions in ventilation systems. The motor, because that's physically making sound since it's moving, and it contributes to fan rotation, which further adds to the sound.
And travels everywhere, so it becomes like an extended, like an octopus in the whole building, like spreading sound. But also in between rooms, I labeled it vent neighbors. Someone mentioned this as well before. I think it was Alexander. Yeah, you can hear the drummer 4 floors down. That's your vent neighbor. Especially when it comes to home hacking, I want to also deal with the vent neighbor sounds as well, for all sorts of reasons.
And then for some sound-modifying actions, the vibrations of those mechanical components, when they interact with the structure of the building, that modifies sound. Additionally, the air movement through the ducts, it creates resonance, and this is called the duct effect. And the air movement through the return vents, which are the vents that are pulling out the air from the room.
And then, we'll get back more to like absorbing sound and sound mazes. Ideally, we could put it about the source and putting like a maze at the source, but we couldn't do that in most places, so we'll be doing that mostly through augmented vents that we'll be showing in a bit. And also playing with filters and stuff like that.
So for some external modifiers, we have wind effects. So when you have strong winds outside, and maybe you guys have experienced this, the ventilation fans, they go into overdrive. And this creates a lot of internal noise. Then we have temperature and humidity, which directly affect the air density. and that also affects the airflow. We also have carbon dioxide sensors, so when the air quality of the room, it drops, the fan speeds up to allow for more air intake, and that also contributes to the sound.
So when it comes to what we can do, again, there's a blurry boundary between the structure and the interior. We ended up mostly doing interior hacking, so at the exhaust bit or the intake bit. And what's interesting sometimes is that, so we're using this idea of augmented vents, so we kind of build out from the wall. As that sort of sound modifying action, what's interesting in the case of, for example, like Alexander's rooms, you have 2 vents, 2 in and outputs, so you can play with both of them, and that kind of changes the whole pipe turbulence that goes on in there. And we tried various things. We tried like inserting sort of mouthpieces to the vents and modifying it in that way. But interestingly enough, just playing with that kind of turbulence was very interesting and made all sorts of cool sounds. So these are the now famous famous vents. So we'll show a few hacks. So what on earth are you going to hear now? We did joke about in the beginning that, well, a lot of people like nature sounds, of course, so complete silence isn't great. So what, could we kind of hack the vents to sound like a nice pouring river or songbirds tweeting and stuff like that? I'm not sure if we managed really songbirds tweeting, but kind of almost in some degree. Like it's at some point makes this sort of harmonic minor scale going up and down, sounding quite cool. But it seems like it sounds like something stuck in the 90s with sort of modem sounds and all sorts of weird stuff, and maybe more sort of woodpecker sounds than fable bird singing. So let's see if we can play this. Oh yeah.
The other one?
It sounds like a modem. Yeah. Loud. It's hard to convey. So sort of nature sounds sound very cool and nice in the moment. I'm not sure how long one could listen to it, but it's very cool. But we recorded loads of this, and like it changed over time as the ventilation changed, turbulence changed, the scale changed. Sometimes it was not in that key anymore. It kind of went down a fifth. So it was very cool. I just couldn't animate more. Oops, sorry. Oops, that's okay, we've heard this. We also had some vent fails. I tried to make a vent kazoo. Almost worked, but it's a prototype still for now.
It didn't sound like a kazoo, but it sounded like something.
It sounded like something, yeah. for future experiments. And let's see. Oh yeah, so now for the sort of home hacks. I got into this from hacking my own home. That's not meant to be there. Sorry, let's see. So we in my flat, I'm at the top building. This was actually, this picture is actually this picture of my flat. My flat, this is me. I'm on the top floor, and there's lots of noise from this crazy fan at the top of the building that sort of vibrates into the whole building and goes right out here, which is, oh, you can actually see my cursor. Well, up there, there's a hole that goes straight in, so it's very noisy. So this is a schematic from how it looks like from above. So you have this vent that connects you to all your vent neighbors. And a massive, I mean, I can't remember the decibel readings, but it was pretty high. And with these ducts, it just goes straight into all rooms without any hindrance. So I tried making a sound maze, like an augmented vent, because I'm not allowed to go in here and do things, by just having ducts go through the maze, and that way air goes through, but sound doesn't. However, the ducts I was using were perforated, as Stig explained, one should not use. So the sound just kind of went straight through, which didn't quite help. So I had to rebuild it all with slightly thinner materials, and then it worked a charm. It's just dead silent. It's really nice. So this is something you can do. Not the prettiest thing, but it was meant to be behind a wardrobe, so it was kind of fine. And I started thinking then about, like, well, how about combining all these things? Because I also record at home, so I needed to build all sorts of absorption panels and stuff like that. And of course, still had my ventilation. And I realized the closest thing we have to some sort of fusion of this is like these rotating lamp fans that you have in warmer countries. We don't have them here. So surely one can kind of combine them in some way. And if you remember this, like this sorted out these two rooms, but the second bathroom doesn't have it just went straight out. So there I had to properly build out again, and that will also be visible. So the question was then how to combine it all. So I combined it by making kind of a sort of a dropped ceiling. And it looked really nice in the end. It's like you get the sound maze, you get a drop ceiling without having to drop the ceiling and put LEDs and stuff like that. And an electrician told me that's a lamp. Because it's not, it's not part of the structure, you put it there, it's a lamp. So I didn't need an electrical sort of certificate thing or whatever. The transformer is actually outside as well, so it's quite easy. You just kind of go, put it up there and it's great. I also built like sound panels on the ceiling, which kind of ended up fulfilling a similar function. This is just a bunch of homemade sound panels put together, as big as I could, so that I could actually flip it around without hitting the ceiling. That was the constraint in this case. And then trying to fit it up on the roof. This is me for scale. And it kind of worked. And it also became like a acoustic, a light, and also vent sort of sound absorbing panel, because there's a lot of vibration in the ceiling. Very low frequency that we didn't really notice, but I noticed when I went under it that suddenly it just cut off those rumblings in the building. So now I just have to put that in the whole flat somehow as the next task.
We also did some more hacky hacks, where we started with mechanical hacks. So the idea was to use low-density objects because that would allow them to move more to the airflow. And we used textured surfaces. So I 3D printed ping pong ball, which wasn't a complete ping pong ball, it was a mesh ping pong ball to allow airflow inside the ball. And I put some beads in it, some embroidery beads. And then I just put it in the system. So it's there, but it's just there, And then I decided to do something with lights, and still using the principle of turbulence. So it's the same ball, but this time it has a light in it. So it's like the ventilation system is breathing. It has a life of its own. And then some more stuff. Just plain old cardboard. And a little filter. This cardboard was taken from a pizza box. Says cheddar. And then I also experimented with positive and negative pressure because we have the supply vents and the air and the return vents. So I stuck a honeybee on a string and I put it in the system. And you see how it moves a bit here, but then I change the pressure, and then it moves a bit more. And apart from that, we also experimented with some digital modifiers. So I used a light-dependent resistor. So imagine you're in a room and the lights go out and something happens. You know, there's a ghost in the room or whatever, and then this happens. So I conveniently placed the speaker inside the duct, so it would enhance the reverb. And for those of you who can read Morse code, this was Morse for help, H-E-L-P. Furthermore, we have not worked on this yet, but the idea is to continue our research, and we might sonify ventilation systems to make the airflow provide information about the time of day. For example, it might slow down at lunchtime, and that would be your cue to go and have lunch. Or we could musicify it. For instance, on Friday night, you might get musical output. Then we could also gamify it. For instance, when you open the door, and you get a personalized greeting from the ventilation system. Or we could make it interactive. So it encourages you to get up and open the door, so it encourages physical activity, and when you do that, then the airflow changes again. That's it. Thank you. Oh, and we do have a hashtag VentHacks, so if any of you experiment with your ventilation systems, please upload to social media, Instagram, Facebook, YouTube.
Yeah, thank you to Maham and Ioannis. And as you see, there's a lot of potential here in hacking and modifying systems. And I guess what we are trying to do with this approach is to say that, well, if the system is there, let's use it for something fun, and let's see if we can kind of make people happier and have a better life through these type of things. Well, now we are at the end of the program. The plan is now to have more of a general discussion. Also now, feel free to share your own ventilation sound recordings. But we could, if there are any direct questions to Ioannis and Maham, we do have time for that before we enter the general discussion. Or?
How long did you put up with your sound before you decided to take the hack?
Did you?
Sorry, say that again. Sorry.
How long? Which hack?
Oh. Let's see. It was pretty much from day one. Yeah, that's one of the things you don't know when you go on Visning. What's it called? When you no, I realized quite quickly that this is not going to do. How on earth can we fix this? So, and I've been joking through the whole process. What if there was like a ventilation conference I could just go to? And it was definitely a rolling joke. So when this came up, you have no idea how happy I was. It's like, oh my God. And then I got dragged into this, probably due to overload of enthusiasm. But I do highly recommend it though. Like, it's an enormous difference, both like aesthetically and sound-wise. And they also checked all the flats for like, do they conform to everything? Because some people put up fans and stuff when they're not supposed to and so on. That's very bad. And then they just looked at all these stuff and they're like, yeah, it's great, yeah, airflow is good, fab. And what I forgot to mention is that a lot of people actually moved out of that building, apparently, because of the noise, which is quite common in various places. So it is fixable. Now I'm lobbying to try and put a sound maze up in the actual source, because I can still hear like a tiny bit of rumble. Normal people don't get bothered, but since I'm already on this quest, I might as well go all the way. So I'll give you an update on the next ventilation conference.
Let's move into the general discussion, and thanks, Maham and Ioannis again. So one of my motivations about organizing this and doing this work is to see if we can improve the world. Kind of that's not a small thing, but ventilation systems is something that we all live with. If we don't have it at home, we might have it in our office, etc. And then, so it is a general interest of mine, and I think to several of you also showing up today here, either in person or online, that this is something that actually matters, and it's something that, in my experience, it's not that much talked about, and also even just kind of trying to find people to invite for this event today, it was actually challenging to find people outside of the really specialist circles for actually doing research on this. There are certain people in the public health sector that have been working on this from again more a public health perspective. But I feel that there is a lot of potential in terms of trying to figure out where to go. And also, just as Natasha asked earlier today, who actually decide on these things, and who do we complain to? And if we do have a problem, I mean, for example, in my office now, I turned my complaints into kind of a research project as such. But not everybody is doing that. But if you're sitting in your office and you feel grumpy or down because of your ventilation system, who do you actually complain to, and who cares, really? I'm not saying that Jens Jørgen in the back at the exhibition will solve this for us, but yeah, any thoughts on how to move these things forward, and how can we get a meaningful, also cross or multidisciplinary discussion going and for moving this forwards? Anyone that wants to take that one? Or Kristin, did you want to say something?
I've often wondered about the training of architects and how much sound is part of their training. Yeah.
It's interesting, and a year ago, I was invited to talk at Snøhetta, the quite famous Norwegian architecture company, and it was interesting when I walked into the huge open space. It was a very massive ventilation system running in the room. It was really kind of really took me when I entered the space, and I spoke to several of the architects there, and they hadn't thought about it before I pointed it out to them, and in retrospect they told me that now they cannot stop thinking about it. So, but Snøhetta is also a company that has been working on also now getting mechanical ventilation back into the new building in Nydalen, for example. So that's an interesting thing, that non-motorized systems, I guess, are reintroduced now also in architecture. But I guess that's an interesting question, really. Perhaps it's a question for you even to talk about the kind of mechanical versus the motorized type of ventilation system, if there is anything going on there now, or in terms of trends or changes.
Actually, I missed two parts in this discussion. It's the producers of these components, and that's the HVAC engineers. They should be in the loop of the multidisciplinary work on this. But it's difficult to get them on the table. We try to make suggestions on projects for improving, but it's very difficult to get them on board. And in Norway we have only one big producer of HVAC systems. The rest is imported products. And the HVAC engineers, maybe from Brekkastrand can support me, but I think they very seldom make predictions on noise, because they don't have no competence, I think. I agree. The HVAC engineers planning the system have very seldom huge competence on acoustics. They plan from what they have good experience from before, not based on calculations, more or less. Yeah. So,
I actually also invited myself to a tour with the ventilation engineers here at the University of Oslo, and they took me to two of the buildings on the main campus, and we walked through the whole system and up on the ceiling, etc. And they showed me how this is working on the inside, and it's a very complex setup, and then they do spend quite a lot of time on fine-tuning it, but mainly worry about the CO2 levels. So it's not much focus on sound and sound levels. So I think that's an interesting thing. And now in our offices now they have put up these CO2 sensors now that can automatically adjust now the opening, I think, of the airflow. And that's excellent, but I think from a sound perspective it doesn't really help very much. So it would be interesting to have a sound quality type of sensor on the wall as well. That could somehow perhaps be used for something. But that's perhaps something we need to develop ourselves, I guess, and suggest to the market to see if there's a market for that.
I guess the idea that you might have a kind of quality sensor, which is a great idea, would suggest that the context that you're in maybe doesn't matter, or that you'd have to find some way, wouldn't you, of understanding how the context then relates to that quality measure. Because I was thinking I recorded a sound yesterday of a ventilation. I'm not going to put it up because it would just take too long to get it on. But it was at passport control coming in as a British person. Sadly, I now spend a long time in passport control due to past stupid governments. And the reason why it drew my attention was that I was stood there for so long and it was quite claustrophobic and so on. And then I got to this point where there was a lovely breeze and I was very aware there was this sound. I was stood by the ventilator. And I thought, actually, I can stand here and imagine this high frequency sound as forest or as, you know, some natural sound. And if, like, when you go into Helsinki airport or something, I think it is, you get bird sound in the toilet or you get images of the plants, those of you that have been there, you could imagine that you could make this a much more multi-sensory environment. And then in that context, the sound is not something to get rid of or to alter, but to frame in a particular way. But then the quality of that sound wouldn't be described by a single measure, because I guess it's, you know, a product of the whole environment. Yeah.
But it's true that just from this hacking we have done, I mean, it is a lot of potential there in terms of turning it into interesting things.
Yeah, thanks. I love that point. And I actually have two questions. Actually, one kind of connects to that. And for the experts we have in the room here, what is the trade-off when you're designing a ventilation system between having a window that you can open and actually letting the real air come in? That's kind of the first question I have. And that connects also to the new life sciences building. Does anybody here actually know about the ventilation system that's being built into this new big building, just a few hundred meters, isn't it? Just across the road here, and the idea of windows versus, or to accompany ventilation, particularly in the summer, when you want the wind to come in and to actually feel the nature, or actually, because I mean, you've got the big rows, but you've also got other sides which open out onto fields. It'd be really interesting if anybody has any insights into this.
I don't know anything about this building here, but we have an acoustician who's sitting here in front of you, but I'm not sure if you want to dare to talk about this from the industry. Yeah. But it's a good question, though, in terms of I guess the problem I've heard with windows, including in this space here, we don't have windows we can open either. And then when the ventilation system is off, we don't get much oxygen in here. But I guess the problem then is that it causes problems with the rest of the system, right? That it kind of becomes imbalanced. But I guess that's dependent on how complex and big the system is. Do you want to? I'm just looking at you for knowing all about this, but no. Yeah. No, it's an interesting question.
I don't know if I should answer that, but I think we should try to get more collaboration with the psychoacousticians if they work on this topic and see what direction we should actually move, and then push the industry. what people really want or not want out of noise.
I think that's because we had when we were planning this workshop, I had a master student that was working with us this spring, and he said that he cannot study without putting on white noise on his headphones. So he kind of, so then it doesn't really matter if you're sitting in a quiet room, if you're blasting yourself with white noise. I mean, then you could equally well have a ventilation system. So it's and then when the sun does turn off, and if you are sitting in a room with many others, then it may be a bit that may also be problematic. So that's why our approach has not been necessarily to remove the sound, but also to see if we can alter the sound and play with it in different ways. But I think this calls for a multidisciplinary approach, and that's also why I kind of wanted to invite this group of people, including also the anthropological perspective, which I think is very important to figure out. Okay, how do people actually think about these things and describe it and feel about it in their lives? Mm-hmm.
Yeah, I mean, this discussion raises the very, in various ways, Nikki's point about the passport queue and the anthropological discussion that we had earlier. It obviously raises the very difficult but deep problem of relationality and the kind of ways of hearing and listening that are involved with ventilation systems are tremendously dependent on context, but also on personal outlook and on the affordances of the system in both relation to our own capacities and intentions. And I was struck. I had thought about writing about submitting an abstract for this conference when it was first announced, and then in the end, for various reasons, decided I wouldn't. But when I wrote, I wrote an abstract and then went and looked around at some things, and I was really struck to find that the paper by Bill Glava called "What in the World Do We Hear?" from 1993, so now 31 years ago, which is a kind of foundational paper, I suppose, in thinking about ecological acoustics, actually mentions ventilation systems. So can I, if you don't mind, I'll just read a short paragraph out of it, which reads as follows, and which contains a statement that both Nikki Dibbin in a paper from 2001 and I in my book Ways of Listening kind of problematize, which is the distinction between musical listening and everyday listening, and the rather polarized way in which Glava sees it. But nonetheless, I think it's an interesting quote. And he writes as follows. This is right at the beginning of that article. He writes, "The distinction between everyday and musical listening is between experiences, not sounds. It is possible to listen to any sound, either in terms of its attributes or in terms of those of the event that caused it." So very closely related to your work, Alexander. "For instance, while listening to a string quartet, we might be concerned with the patterns of sensations the sounds evoke, brackets, musical listening, or we might listen to the characteristics and identities of the instruments themselves, brackets, everyday listening. Conversely, while walking down a city street, we are likely to listen to the sources of sounds, but occasionally we might listen to the world as we do to music, to the humming pitch of a ventilator, punctuated by a syncopated bird call, to the interplay and harmony of the sounds around us. This may seem an unusual experience, but hearing the everyday world as music is one way to understand what John Cage, for instance, is attempting in his compositions. He is trying to evoke an experience of musical listening to non-musical sounds." So, end of quote. As I say, as others pointed out as well, I think that distinction between source-based listening and listening to qualia, one might say, as a distinction between musical and everyday listening is a deeply problematic distinction. But the change in perspective that Glava is drawing attention to, I think, is still an extremely relevant one. Actually, as Audun's film this morning brilliantly, I thought, showed that by giving the ventilation system agency and a voice, suddenly we see all sorts of benign things going on in that system that we might not have paid attention to. So I think, perhaps sort of riding a hobby horse around the room slightly, I do think that approach, the kind of ecological approach to thinking about the whole ecology of ventilation systems in terms both of the context they're in, what they are doing, what the ventilation systems themselves afford, and to whom they afford those things, is one way of kind of negotiating this highly relational space. Yeah.
Thank you. I read that paper a long time ago, but I actually didn't think I remembered that there was any ventilation system in Guillebaud's work there. Any other thoughts and reflections?
That was actually a great point, thank you. And I was thinking also that who makes the decisions in these places, right? So I think we need to talk about the power as well, which sort of it reminded me the book by The Politics of Noise by Attali. I'm pretty sure a lot of people knows about that. Yeah. Where Attali talks about that. In that one is more about the the power to be able to make sound, and the power to be deciding on which sounds that are around us. I think that really connects to the engineering as well as the institutional decisions and such. And I really like the approaches in the last presentation where they took the action to change the environment in the way that they like. And it made me start to think about, for example, we could set up the temperatures of our rooms as we prefer, right? We have that sort of, let's say, democratized in some ways, that you may prefer a colder environment, maybe I prefer a couple of degrees more. And then I started thinking about okay, then how would we do that with the ventilation sounds? That approach was super cool. In the last presentations, they were like, I want to have a light that's sort of like breathing. And the other person was like, I want to change the pitch a little bit. And then someone else was like, I want to have actually this more quieter and less rumbling. Or maybe someone else prefers a little bit more rumbling and then a sensation feeling with it. That's what they prefer. And I think a knowledge on that would be great. I think that's not out there yet. Maybe a bit more experimentation is a really, great possibility here.
Well, that's why we're calling for the ventilation hacks, so that you can all kind of contribute your own things, just in a way that you can buy. How many different colors or kind of mobile phone covers can you buy, right? I mean, one size fits none, right? We could kind of personalize and kind of sell these different things. Maham can set up. She has a bachelor in finance originally, so she can set up a business in terms of selling these kind of vent covers. for I said, try to see if there's a market for it after your PhD. Yeah. Any other thoughts or comments?
Thanks a lot. It's just one question emerged for me. Do we have a typical definition of what is a ventilation system? I was very interested when you told this is connected with oxygen. And it made me think there are plenty of social activities connected with oxygen. So with technical displays, I mean fan system, air conditioning system for other countries. But there is also wind instruments and also the anthropology of breath. All human activities connected with breathing. It would be interesting to maybe keep the frontiers larger. I don't know, not in a short time, but maybe in a programmatic project to have more possibility of comparison or something with breath. It made me think, because of your suggestion, that was interesting.
No, it's really about airflow, I think, in different ways and shaped in different ways as well. And it reminded me about last year I visited Eric in Oxford, and I stayed at Wadham College, beautiful place. 400 centuries old or so, the building, yeah. And out in the corridor, it was a window that wasn't entirely tight. And it was quite windy, it was blowing, and you can hear this whistle through the window, right? And I actually stood still there out in the corridor. I'm not sure if I told you. So I have a recording of that as well, which was this beautiful kind of whistling sounds, a wind going through kind of a small crack in the window, right? And it's these type of things, I think these are important, and I guess one of the challenges about standardizing everything that we have now, our systems, and making it so perfect in a way is that we forget about some of the joys of these kind of imperfect, kind of old school, you could say, ventilation systems. But also in my own house, I live in a house that's 100 years old, and there we have a mechanical system, and in the bathroom you have kind of intake, and you have going out on the top, and when it's windy, you really hear it, and it's a very interesting way of feeling that you connect to nature in a way that we don't really get in a very kind of tight system that we have in this building, for example.
I don't know if I can move on to a sound recording of a ventilation. So it picks up on your point about breath, actually. So, because I also thought, where are the limits of a ventilation system? And actually, the word ventilator took on, in the UK at least, an extremely different meaning and connotation during the COVID crisis, where people who were dying or would otherwise have died were put on ventilators. So I've got a sound, I don't know, it's got a mini jack connection, or shall I just play it from?
Perhaps it's just better
to play it from this.
Play it from that, and just hold the microphone in there.
Yeah. So that kind of slightly, I hope not too personal recording. So about 2 or 3 years ago, I was diagnosed as having a condition which is called mild sleep apnea, which is mild obstructive sleep apnea, I think is the full term. So I occasionally, when I'm sleeping, stop breathing. And it's supposed to be, it's not great for one's mood when you wake up, and it also has long-term health considerations. So I was diagnosed with it, and one of the approaches to combating it is to wear what is called a CPAP machine when you're asleep. And a CPAP machine, which stands for continuous positive air pressure, is a bit like a ventilator. It's a mask that you put on over your nose and mouth, and you wear it when you're asleep, and it provides a certain amount of positive air pressure which keeps your airways open, which otherwise might close. So I made a recording of myself. I'm not actually asleep. This is a kind of simulation, as it were. And what you'll hear is, of course, well, 2 types of ventilation going on at the same time. One of them is the continuous sound of the CPAP machine, which is basically silent, except that a certain amount of air inevitably leaks around the mask. It doesn't fit the face absolutely tightly. And the other is my own self-ventilation, which is my own breathing. So I'll see whether you can hear this. That's enough to give you a sense of it, if I can stop it. And I suppose for me at least, so I was thinking also about the aesthetics of it. And although I know aesthetics is not only about value, it is partly about value as well. And this, for me at least, has a kind of double value, because on the one hand, it's a kind of a health support, but on the other hand, it has, undoubtedly a kind of medical, both sound and connotation for me. I don't particularly like wearing the mask. I don't always wear it, and that combination of a kind of continuous whistling, which has a slightly, for me, perhaps because I know what it is, has a slightly menacing quality about, or a sort of not a positive property, but then the breathing arguably does have and so on. So I found it quite an interesting way of thinking about the kind of entanglement of artificial and living ventilation systems.
It's a very interesting comment, and also in terms of some of the other projects we have been doing at Ritmo, where written is something that we care about. It's also to explore how rhythms, and particularly musical rhythm, but also non-musical rhythms influence people. And this is also actually where my Standstill project started, was really to look at that. And Arthur didn't get into this now, but we also have recordings of my physiological data also from last year, so we'll look more at that. But there also the aspect of breathing, respiration, that we have been working on also now at Ritmo in various ways. It's very interesting to look at kind of different types of entrainment, as we call it, between external stimuli and what's going on in the body. And this is an extreme case, I guess, of entrainment in a sense between machine and human, but also in other ways to think about how could we possibly also cause some kind of entrainment with also even a ventilation system if it was interactive somehow or kind of responded to us, not only being a passive thing that can kind of blowing into the room from outside. But this is very speculative, of course, but interesting things to at least let's think about. Well, have we gotten to a point where we want to be even more speculative and exploratory down at the coffee machine and also with some refreshments? Sounds like that. But then I think we'll close the session here and say goodbye to the people online as well, and we'll move down to the Ritmo kitchen. Thanks a lot for all the presentations today. I think this has been amazing. I've got so much feedback from people all around the world when I announced this thing. So this definitely shows that there is an interest in this. Nobody really knows exactly how to tackle it, but there's an extreme interest in this topic. So that's promising, I think, for future research. And well, we'll see if there will be a second edition or not of this workshop, but at least this was a really, really fun day. So thanks a lot for all of you for contributing, and let's continue down at the coffee machine.